them, with 3 lithographed plates depicting 26 figures, according to personal experience and the latest scientific findings by Dr. Eduard Assmuss. Berlin. Parasiten der Honigbiene by Eduard Philibert Assmuss, produced by K.D. Thornton, Hagen von Eitzen, Marcus Brenner, Agnetha Dyke, and the online distributed proofreading team at http://net.jgp.net. Parasites of the honeybee and the diseases caused by. Explanation of the illustrations. Published by Ernst Schotte Company, 1865. Plate I, Fig. 1-1. Fig G, 1a. Primitive larva of Meloe, cicatricosis. Fig O. Sensory horn of the same. 2. The second larval form of Meloe cicatricosis. Leech, Fig 3. Pseudochrysalide of the same Meloe species. Fig G, 4. Nymph of the same Meloe species. Fig G, 5. Female fig, Meloe variegatus, Donovan. 5a. Sensilla of Meloe variegatus, Donovan. Fig U, 6. Meloe proscarabeus, Linnaeus. Female fig. 6a. Datwone. Male Sensilla of the same species. Fig U. 6b. Oral Dong. Table 2. Female Sensilla of the same species. Fig U, 1. Fig U, 1a. Larva of trichodes, Apiarius, Linnaeus. Foot of the same larva. Fig U, 2. Nymph of trichodes, Apiarius, Linnaeus. Fig E3. Fig U, trichodes, Apiarius, Linnaeus. 3a. Whirl. Sensilla of trichodes, Apiarius, Linnaeus. Fig 4. Larva of Phora incrustata, Meigen. Fig V5. Pupae of Phora incrustata, Meigen. Fig U, 6. Fig E8, 8. Phora incrustata, Meigen. Fig 7. Larva of Braulicoica, niche. Braulicoica, niche. Fig U, 8a. Da. Leg of Braulicoica, niche. Table the 3rd. Fig U, 1a. Einmann. 1. A young larva, Gordius subafertus, the Siebold. Fig U, 2. Terminal part of a male Gordius subafertus, de Siebold. Fig U, 3. Myrmis albicans, de Siebold. Natural size. Fig G4. Tail of a female Gordius subafertus, Siebold. Fig U, 5y. Mucor melitophorus, Hoffman. Note, IDOI, by parasites. In the strict sense is meant any living being animal, plant occurring on or in another living being, and feeding upon its juices. Such a mode of life should not strictly be labeled parasitism. But not so the larvae of meloids, which use the bee only as a medium to reach the beehive, where, having arrived, they leave the bees, first feeding upon bee eggs and then living on bee bread. Thus, among the parasites of the bee, we would include all animals and plants which occur on or within living bees, or their larvae, etc., and feed upon their juices. Hence Braulicoica, which lives on the bee and feeds upon its juices, as well as Myrmis albicans, which resides inside the bee and consumes its fat, are parasites of the bee. The larva first appears in the hive as a predator by consuming a bee egg, and later lives on the collected and prepared products of the bee. This second lifestyle of the animal is better distinguished from actual sponging off others with table scraps. Similarly, the larvae of trichodes, in the described sense, are not to be considered parasites of the bee, but as predators that stalk the bee brood in the cells. If the bee larvae were to emerge freely outside the hive, the trichodes larvae would certainly follow them outdoors, much like the larvae of Colosoma inquisitor or Colonel Sycophanta chase caterpillars on the ground in trees. If one includes the trichogram larvae, which is certainly correct, among the parasites, then by the same logic one should also include the Colosoma, and generally all Carabidae larvae, as well as their imagos. Yet no one has suggested classifying these animals as parasites. However, this would expand the term parasite to most animals, and for example one could argue, based on analogy, that lions, river otters, and others, all carnivorous and insectivorous predators, should be considered animal parasites. Herbivores that feed on living plants should be labeled plant parasites. The parasites are classified as ectoparasites, external parasites that live on the surface of a host, and endoperites or entoporous internal parasites that occur within a host. Therefore, when I list the mellow and trichogram larvae here among the parasites, it is partly because prominent zoological authorities still consider these organisms to be parasites, and partly because they cause disease symptoms in bees, which is a topic addressed in this work. They are further distinguished as temporary or occasional parasites that only visit their victims for a short time to feed on their juices, such as fleas, mosquitoes, etc., and as permanent parasites that inhabit their host for an extended period, or even throughout their entire life. The number of animal parasites in our honeybee is not particularly large compared to some other bee species, such as bumblebees. Therefore, permanent parasites are divided into two forms, lifelong and periodic, depending on whether the parasite remains in or on its host throughout its entire life, or is only present until it reaches sexual maturity or sheds its juvenile form, and then migrates again. If we exclude trichodes and mellow, only 4 genera with a single species remain, namely Phora incrustata, Braulicoaca, Gordius subafurcus, and Myrmis albicans. 2 all other arthropods found among bees, such as wax moth larvae, sawdust beetle larvae, etc., are not parasites. Gamesis coleopteratorum. Similarly, the bee brood or pollen mite is not a parasite because it does not obtain its nutrition from the body of the bee, but feeds on pollen. Lin. A common mite found on bumblebees and beetles is definitely not a parasite of the bee, as this creature only accidentally gets onto a bee and seeks to quickly leave it. Doubtful parasites in the generally accepted sense of the honeybee are the larvae of Trichodes alvarius fabro. 3. It now leaves little doubt that more parasites on this hymenopteron will be discovered in the future, which occur very frequently in the nests of the mason bee and may also, since the larvae of its relative trich, Apiarius lin, are found in beehives, disturb our honeybee, and the larvae of Ceropulpus barbatus shoal, a beetle belonging to the family Melendriidae. For example, it is easy to assume that Gordius aquaticus and Myrmis nigrescens, which indeed occur without distinction in various insects of all orders, will also not exclude the honeybee. Of the 4 parasitic species mentioned above, the first 2 belong to the order Diptera and the last 2 to the order Nematoda. Only one parasite, Braulicoaca, lives as an ectoparasite and, to use Lecart's classification, is a permanent stationary one. 4. The remaining 3, Phora incrustata, Gordius subafurcus, and Myrmis albicans, are endoperites and periodic stationary. Only thus could I depict all the metamorphic stages of this beetle family. However, given that the primitive larvae of the genus Meloae are so similar, it can be assumed that the further metamorphic forms, the pseudochrysalide, the second larval form, and the nymphs of the other Meloes will also correspond to those of Meloae. Cicatricosis. All illustrations are greatly magnified. That I have included in the illustrations images of the larvae of Meloae cicatricosis at all its stages, an insect that has not yet been observed on the honeybee, should not be blamed. For as to Meloae variegatus and M. proscarabeus, provide fragments, since the further metamorphic forms of these 2 Meloae species are not yet known. The author, Leipzig, March, 1865. The trichoduce lark and nymph, the phorolarv and pupa, as well as the larva of Braula and Myrmis albicans, were designed by me. The remaining figures are borrowed from the works of Newport, Fabre, Brand Ratzeburg, Meigen, Zenker, Meissner, and Leckart. Arthropoda.ul. Insecta, class.u. Jointed-footed animals. Order. Beetles.org. Coleoptera.norn. Eleutherata. Fabricius. Family. Ladybeetles.to. Claridae. Westwood. Westwood. Descriptions of new species of Claridae, etc. Proceedings of the Zoological Society of London, 1852, p. 34, 1856, p. 19. Characteristic features. Clarides, Latrelli, Genera Crustaciorum et Insectorum, Vol. E. 269. Most medium-sized, or smaller, brightly colored, red, blue, metallic, glossy, beetles with a slender, almost cylindrical tapered, relatively soft-skinned body structure. The chin is four-sided. Mandibles have two front lobes, often bale-shaped, occasionally elongated oval, pointed, or cylindrical at the end. The head is large, of the width of the thorax, protruding more or less from it, with a separated head shield and a distinct upper lip, powerful, sharp, mostly toothed at the inner edge, and equipped with a membranous fringed margin. The tongue is partly skin-like, partly horny, the front part expanded into two rounded folds, flatly flanged and fringed at the front edge. The lateral tongues are clearly indicated by oblique, fringed ribs. Lipped tasters tri-segmented, often with a bale-shaped final segment that is not uncommon longer than the jaw points. The antennae emerging before the eyes on the side of the head, 11 segmented, the first segments round, or inversely conical, significantly thickened. The eyes inner rounded, unequally faceted and combed, coarser and finer. The neck shield cylindrical, largely narrowing towards the rear, from the base more or less constricted, usually narrower at the base than the wing covers. The underside of the forebody formed from the turned-back edges of the neck shield back, and the front body, which is more or less strongly fused with it. Joint depressions of the hind hips widely opened at the rear. The sternum, episterna, and epimera of the middle body distinctly separated. The wing covers completely encompass the posterior abdomen. The episternums of the posterior thorax are long, narrowing slightly towards the rear, covered by the epimeron from the edge of the wing cover. The posterior hindquarters are deeply embedded transversely, covered by the thighs. The anterior hindquarters are cylindrically conical, protruding somewhat, with the middle ones shorter and almost spherical, usually bearing more or less separate joint rails. The tarsi are 5 or 4 segmented, provided with leather adhesive pads. The abdomen consists of 5 to 6 abdominal and 8 dorsal rings. The last ring, the anal ring, is equipped with a horny shield at the rear abdomen, bifurcated. The anus projects as a plug-like appendage. 9 air holes present, 8 on the sides of the first 8 abdominal rings, the 9th on the underside of the central breast ring. The larvae are elongated, flattened, with 13 rings including the head, usually fleshy, yellow or lighter or darker red colored, with a horny horizontally extended, flattened head, a large horn plate on the anterior dorsal ring, and 2 small platelid on the anterior dorsal ring, and 2 small ones on the middle and posterior thoracic rings. Upper lip protruded, shorter than wide, with a notch at the front. Mandible quite short but robust and sharp with a sickle-shaped tip. Lip sensors 2-jointed. Lower jaw fused with the chin, closely articulated next to the lower lip with 3 joints. Antennae short, arising immediately above the articulation of the mandibles, 4-jointed. Side eyes 5 on each side in 2 rows, the front ones consisting of 3, the rear ones of 2. Legs relatively short, or also impressive trichodes, composed of 3 joints and clingy. Lifestyle: the beetles are found on flowers, or beaten old wood, on rotting tree trunks, and some also on cadavers. They feed on the anthers of flowers, but their main food should probably be of animal origin. At least I have observed trichodes apiarius on umbel plants catching and devouring a syrphid larva. The genus Clarus is already known to pursue various insects, especially wood insects. 5 Corynetes ruficalis was also found on dead snails. The larvae of these beetles mostly live under the bark of trees in decayed wood, where they chase and consume the larvae of other insects. Some of them live in bee nests, feeding on their brood. Others still feed on carrion. Geographical distribution and number of species. The family Claridae comprises around 500 different species, 8 genus. Europaea 7 has 40 good species, of which the German fauna includes 11 species with some varieties. 6, and is distributed throughout all parts of the world, particularly rich in the tropics, notably in America, where almost half of the known species occur. Trichodes, Herbst. Beetle, Herbst, natural system, etc. Beetle, a 4, p. 154. Upper lip, almost quadrate. Mandibles, tri-toothed at the tip. Lower jaw with 2 fringed plates and thread-like lip whiskers. Characteristic: middle-sized, varying greatly in size within the same species, mainly dark blue or greenish beetles with red-blue banded or vice versa, blue-red banded wing covers, chin narrow, antennal taser with an extended terminal segment, tongue widened forward, rounded on each side, notched on the front edge. Lip whisker somewhat larger than the lower jaw, with a reversed triangular terminal segment. Eyes strongly triangle-shaped. Antennae quite short, with a 3-segmented triangular, flattened club. Torso cylindrical, narrowing towards the rear. Wing covers extended, equally broad, pressed downward. Stout legs, 5-segmented feet, the first segment very shortened and barely visible. The following segments, except the last, with broad soles. The final segment is the longest, as long as the rest combined. Lifestyle. The larvae, known only from 2 species, Trichodes apiarius and Trichodes alvarius, correspond to the characteristics mentioned in the family description. They are rosy red in color, and less slender than those of the genera Claricentilus. Beetles are usually found on umbelliferous and spiraceous plants, where they feed on the anthers of these flowers, but mainly, as already mentioned, on other insects that they chase on these blossoms. Their larvae live in the nests of various bee species, Osmia, Megachile, Apis, and feed on bee larvae and nymphs there. By the way, it seems that at least the larvae of Trichodes apiarius do not strictly adhere to taxonomy, but also eat larvae that are not part of the bee family and are quite distinct from them. According to my observations, the larvae of Trichodes apiarius live in wood within the galleries of Syrinx larvae, which they pursue and consume, particularly the younger Syrinx larvae. Experiments I conducted with confined trichodes larvae demonstrated that not every insect larva is consumed by them, unlike most Carabidae larvae. For example, small Nematus salicis larvae were left untouched, as were small Plutia gamma caterpillars. However, they readily fed on Aphis pruni, and also consumed dead worker bees, Trichodes apiarius, Linnae. Bee beetle. Common flying beetle. Plate 2. Figs. 1-3. Page.war. Herbst. Natural system, etc. Beetles. IV2. 156. 1. Tfdoi. 41. Fig G11. Februar. Cyst.on. Eluth. Tom. I. Page 6. 284. Shown. Cyst. Insect. Dart. Tom Tutty. 48. Page.1. 6. Sturm Deutschel. Fawn. G1. BD. Page or 24. Clud Clarii Page 74-2. Spinola. SI monograph. Sur le Claritum. IPG. 305. 7. Eric's Cording. Ins. Deutschel. BDI. I feel. BRB.E. VVD. Kiesen. Page. 689. 3. Nature Dorting. Attilibus apiarius, Linnae, Sistor. I2. Page. Dial. 260. 10. Clerus apiarius, Illig. Kef. Prius. Tom. I. Page. 283. 3. Olive. Entom. Tom. I. Fee. 76. Darrow. PL7, 4. Taepe. I. Figi 4. Pans. Fawn. Way. German.u. Page 31. 13. Rossi Fawn. Etrusc. 138. Tom. I. Page 353. Die Larve, Swammerdam, Bibel der Natur, Pag, 210, TIF, Fijoro, 26.0. Third. A, B, C. The third. Reomor mem, etc. Fear. Tab. 8 subnomini trait. Alvarius. Length 5 to 6, width 1.76 to 2.5. The larvae fig. 1. Teophae. Are pinkish red with individually standing brown hairs. Characteristic shiny black blue, densely dotted, rough-haired, wing covers slightly extended at the back, coarsely dotted, bright red with dark blue tip, and two such bands that spread out widely or narrow down, or the first band dissolves into individual spots, and is absent in rare cases. Head, thorax shields, legs, and posterior comb brownish. Length 6 to 7, width 0.5. At the last body ring there are two upward curved fleshy anal spines. The nymph fig. 2. TFST is yellowish-white, covered with fine, long yellowish-red hairs on the head, abdomen, and back of the hindgut. Length 5, width 1.75. Lifestyle. The beetles are found in May and June in Russia, the northern and middle regions, also in July, on various flowers, particularly umbellifers, spiraceae, and also composites, often quite frequently, by working bees. The bees and nymphs only graze them. The bee larvae are completely consumed. As for the parasitism of the larvae in beehives, they are found in Russia from July to May of the following year in uncleanly kept comb structures on the ground, where they hide in the cracks like earwigs and wax moths, larvae, and occasionally emerge to eat half-dead or dead bees, as well as bee larvae and nymphs that have been dropped to the ground. Once the trichodelph enters the hive's brood in a brood table, the bees would find it difficult to extract the larva. Another crawling into the beehive to observe the bee brood, I was unable to do, but I do not doubt that it could happen if a hive is weak and its occupation is insufficient. For after the larva bites into a sealed brood cell, it continues drilling sideways along the cell floors into the brood, forming formal passages in all directions, but without consuming the bee nymph first, rather pushing itself underneath the nymph first, without hurting them, and then begins its feeding at the center. This is how larvae behave, as I observed in a small offshoot from a brood comb with about 200 bees. The beetles probably lay their eggs outside in the cracks and crevices of the beehives, and in weak hives, they may also enter the interior. At least I found a Trichodes apiarius in a young hive with little brood last July 1863 on the bottom board, where 4 yellow round eggs about the size of a poppy seed were also found among the debris. A section of the beetle also provided no insight, as the ovary only contained undeveloped egg sacs. Unfortunately, the eggs did not develop but shrank and dried out, which, however, left it undetermined whether the eggs really belonged to the mentioned beetle. Yet, I believe I can assume that the eggs belonged to him because, after all, the beetle had no business being in the beehive other than to place his brood in a suitable location. When the larvae have emerged from the eggs, they will most likely, if the conditions of the hive permit, i.e., if the hive is not too weak and does not exclude foreign animals, very soon go to the brood compartments to establish their residence there. The larvae leave the wax construction as soon as there is no more brood in the hive, and retreat into the cracks and crevices of the hive, where they overwinter. I had small larvae, a little over 1 line in length, which must have just hatched from the eggs, but when I gave them a piece of a bee brood comb, they immediately, as mentioned above, bored into the brood compartments. In April, they start to spin cocoons again, which they continue until May, at which time they have reached maturity. Now they transform into the earth, where they create a smooth cave inside, lining it with a web, and after 3 or 4 days, they transform into nymphs. After 35 or even 30 days, the initially yellow beetles develop ... However, some larvae also seem to pupate in September of the same year, and overwinter as pupae, after which the beetle appears in May. A piston significance. In my case, fully grown larvae that I found in tree trunks, in the galleries of Syrinx larvae pupated in September of the same year, just like Swammerdam LC. Mentioned nymphs taking a long time to develop into complete insects. He gives a full year for nymphal dormancy. Remains unclear to me. In general, the trichodes larvae seem to cause little or no harm to bee colonies, except for weak colonies that do not block their access. Only when they occur in large numbers in a colony, particularly in the brood nest, can they weaken the colony through the tunnels they make, with each larva tearing out 100 or more brood cells next to the floor. By the way, the beetle is not particularly common, and its brood relies not only on the honeybee but also, and more frequently, on other bees and hymenopterans. This causes much work for the bees because the capped pupae, when the cell walls they are in are chewed through by the trichodes larvae, DA, and can lead to what is known as the non-contagious American fullbrood. Against this, the trichodes larvae in France appear more frequently in beehives, at least Paris. Tatu Elbion, P619 mentions that the larvae are known by beekeepers there and are called vers rouges. Family. Regular cleaning of the hives, removal of debris, and similar measures are the best preventive methods. Prophylaxis. A rational beekeeper who keeps beehives with removable frames will hardly ever suffer harm from this insect, as he will not allow it to appear in the hive. Vesicantia. Mulsant.u. Blasting beetles. Cantharidiae latrale. Vesicanti. Mulsunt. Histoire naturelle des Coléoptères de France. Characterization. Medium to large, green, blue, black, often metallic glittering, and sometimes brightly colored beetles with a soft, leathery body structure. The head is large, usually broader than the neck shield, lowered, heart-shaped or three-sided, extended and broadened behind the eyes, then strongly narrowed down in a neck-like manner. Upper jaw simply pointed. Lower jaw with horny plates, often fading inward. Jaw tasters thread-like. The last segment barely thicker, round or rounded off. End segment of lip tasters widened, truncated. Eyes mostly transverse, sometimes with a border. Antennae usually 11, occasionally 8 to 10 segmented, thread-like or snarled, or also short and bulbous. In some species the scutum is absent. Neck shield cylindrical, roundish or four-sided, usually broadened behind, narrower than the wing covers. Metathorax extended, rarely very short. Wing covers flexible, often not fully covering the body, in some even shortened, standing apart from each other and then with missing hind wings. For hips very large, tapers downwards in a spike shape. The middle segments are usually removed from the rear, less frequently covering them. The hind segments are approximated to each other. Foot joints heteromerous, usually undivided. Claws split. Abdomen with 6 to 7 free abdominal rings. In anatomical terms, the genus Mello, Lida, and Mylabris from the family Vesicantium have been fairly extensively studied. Mello, in particular, by Brandt and Ratzeberg, 11 Newport 12, and more recently also by Lady. 13. All three genera of this family agree essentially with each other, so that the genus Mello can be considered the basal type in this regard. Of particular note from the nervous system is that the optic lobes are clearly distinct from the brain and exhibit some dark purple, at least in Mello pigment spots. Otherwise the neuralem is yellowish-red in Mello. Thoracic ganglia are 3, broader than long, with a lateral nerve running from each longitudinal commissure between the first and second nodes. From the third node, 2 stronger and 8 weaker lateral nerves arise, as well as a nerve plexus that Leydig is mentioned above. Page 287, considers sympathetic. Abdominal ganglia are 4, elongated oval, with the last one being the largest, elongated and rounded at the back. The commissures between them are very long. 2 lateral nerves spring from 2 of the 3 front abdominal ganglia overlapping. Sympathetic side ganglia are white-gray. A sympathetic medial ganglion appears as a stalked sac on the front edge of the second abdominal ganglion, between the 2 longitudinal commissures. The circulatory and respiratory systems in vesicantians show no particularly significant differences from coleopterans in general. The esophagus is short, expanding posteriorly, and presenting a more or less distinct constriction by the cardia, a sort of stomach, with clear longitudinal folds. The stomach is large, elongated, cylindrical, internally ribbed with traces of villi, clearly distinguished from the smaller intestine. The intestines make 3 turns, with 4 Malpighian vessels at the second bend. The rectum is distinctly constricted. The ovaries are berry or grape-shaped, with numerous oviducts containing several thousand eggs in a fertilized female. 1 accessory gland. Sperm sac with an accessory bladder. The paired testicles are round, with thin, very long spermatic ducts, and 3 pairs of tubular accessory glands, emptying into the ductus ejaculatorius, 1 pair particularly long and intricately twisted. The ductus ejaculatorius is several times coiled at the back. The larvae of vesicantians are known from Meloe, as well as Cantharis, Apellis, and Sitaris, and they agree in their development and lifestyle to a great extent. They are young with horny, elongated, flattened bodies, sharp mandibles, 3 segmented feelers with a long terminal bristle, 2 to 4 ocelli, a pair of half-body-length legs spread widely apart, a pair of prolegers, and long bristles emerging from the terminal segment used for jumping. Later they appear thick, bloated, soft-bodied, and more or less similar to the larvae of lamellicornians. Lifestyle: the family Vesicantium is phytophagous. The beetles are found on various herbaceous plants, less so on trees and shrubs. Some appear in large numbers, while most occur sporadically. They mainly feed on leaves, some also on the anthers of flowers Mylabris and Sericoma. I frequently encountered on the flowers of Labiatae and Umbelliferae, as well as on Spiraceae, whose stigma bags they gnawed off. Their appearance time varies greatly. Some are more common and even only found in early summer, while others are more prevalent in late summer and into autumn. Most of them contain a very sharp, blistery substance called cantharidin, which oozes out from the joints of their legs as a yellow liquid upon contact. Larvae of certain species, through their occasional presence on bees, particularly those of Melo, also on honeybees, have a detrimental effect on them, and thus on humans. To lay their numerous eggs, the females dig a hole at any location in the ground, usually close to the root of a plant, deposit the eggs in it, clumpwise, and cover them with earth, or they lay the eggs in close proximity to beehives. The beetles are mostly harmless little creatures that cause no harm, but many of them prove highly useful to humans through their blister-inducing and other properties, and are therefore used in pharmacies, notably the genus Cantharis 14, as well as Athis, Melo. Although the latter is now obsolete, it is seeing a resurgence in recent times. 15 only. In the first case, after emerging from their eggs, the larvae immediately set out in groups or larger parties towards various flowers of low-growing plants nearby, especially composites, among the bees in the blossoms. Once inside the hive, they leave the bee. In the second case, the emerged larvae directly head for the beehive. Here, their first food is a bee egg. When a bee lands on the flowers with the larvae on them to collect honey or pollen, the larvae quickly try to climb onto the bee's thorax to attach themselves, or they may even bore into the bee's rings or joints, allowing themselves to be dragged by the bee into the hive. If the larva has consumed a bee egg, it molts, losing its former paradoxical shape and taking on a caterpillar-like appearance as mentioned above. From then on it lives in the beehive until its pupation, feasting on pollen and honeybee bread as a servant to the bees. However, from this second larval form, within the same skin, a horny pupal form emerges without any locomotor organs, which Faber 17 calls a pseudochrysalis, and which, like the nymph, takes no food and remains at rest. After some time the horny skin lifts again, giving birth to a third larval form, another soft-skinned one very similar to the second larval form, also feeding on bee bread, which finally transforms into a true nymph from which the beetle emerges. It thus undergoes 4 stages before transforming into the true nymph. 3 as a larva, and 1 as a pseudochrysalide. This remarkable transformation, which has not been observed in any other insect except this beetle family 18, led Fabre-Lac, Cit. P. 364, to name it hypermetamorphosis. Geographical distribution and species count. The family is represented worldwide and is particularly numerous in warmer regions. Europe counts 103, 19 different species with many varieties. However, only 21 species are found in Germany. 20 genus. Meloa. Linnae. Maybug. Linnae, Systema Naturae. Walder-Thuer. P. 696. Characteristics. Relatively large, thick, wingless beetles with shortened wing covers and a dark metallic sheen. The head is broader than the thorax, triangular. The final segment of the mandibles is egg-shaped, feathery with 11 segments, thread-like, longer in the male, and often irregular due to a larger middle segment. Eyes transverse kidney-shaped. The head shield small, round, or trapezoidal, not widened at the back. Absent of spots. Wings absent. Metathorax very short, wing covers shortened, but sometimes as long, or even longer than the abdomen, rounded, broad at the front, overlapping at the base and diverging gradually towards the ends, mostly wrinkled. Legs relatively short, strong, compressed. Hind legs covering the rear ones. Tibiae triangularly expanded towards the tips, claws of equal length. Abdomen oval in outline, often worm-shaped, thick, soft, composed of 6 ventral rings. 24. The larvae of Meloe have been known for a long time in their juvenile form, from several species, and by some naturalists mistakenly introduced as a separate genus and good species into the animal kingdom. 22. Its other metamorphic forms are known only from Meloe cicatricus, whose natural history has been primarily treated monographically by Newport 23 in Fabre. Compare Fig. 1, Table I. The head is broad, flattened, with a rounded front margin. The upper jaw slender, almost half-moon shaped and pointed. The primitive larvae, as described for the family Vesicantidae in general, are horny in consistency, elongated, flattened, with 13 rings, sharp curved upper jaws, 3 segmented feelers equipped with a long bristle at the end segment, 2 tuta, ocelli, widely spread legs with sharp claws, and 4 long bristles arising from the terminal segment. The lower jaw thick, with 3 segmented palps. The feelers are 3 segmented, the first 2 segments thick, the tip segment thinner with a long bristle. Eyes ocelli. 1 on each side, lying behind the roots of the feelers, prominent, large, round. The 3 breast rings are square, with backward-directed bristles above and on the sides. Legs widely spread, hips strong and short, thigh ring clearly formed, thighs strong, shins long and slender, feet equipped with lance-shaped claws, each side with a movable spur. Last segment with 2 posterior protrusions. Abdomen 10-segmented, straight, narrow, spindle-shaped, with strong, stiff, backward-directed bristles on the margin of each ring, among which the 4, the penultimate abdominal segment, are particularly long, especially the 2 inner ones. 10 pairs of stigmas present, 1 pair on the second breast ring, 9 pairs on the abdomen rings. Those of the first abdominal ring and the metathorax are larger than the others. Second larval form cf. Table I Fig. 2. The head is horny. Upper lip prominent, trapezium-shaped. Mandibles strong, short, blunt, slightly curved, dwindling, and each internally equipped with a wide tooth. It possesses the entire external shape of a caterpillar, is soft, fleshy, blind, covered with very fine, only visible under a lens, downy hair, including the head with 13 rings, of which the metathorax and the first 8 abdominal rings bear 8. The stigmas. The last pair of abdominal stigmas are slightly smaller, maxillae and labial, palps 3-segmented. Antennae bent at the base of the mandibles, 3-segmented, the first segment thick, spherical, the following much thinner, cylindrical. Legs short but quite strong, provided with a powerful claw, suitable for crawling and digging. The pseudochrysales is 13-ringed, horny, with a thick, plump, somewhat curved body, strongly convex on the back, flat on the belly side. The back and belly sides are distinctly separated from an outstanding, framed protuberance. The head represents a mask with some immobile eminences corresponding to the future parts of the head, indistinctly pronounced. Legs are absent, instead replaced by 3 pairs of tubercle on the thorax segment. Stigmas are 9 pairs, equally distributed, as in the second larval form. Compare Fig. 3, Table I. The nymph lacks any special markings. The third larval form corresponds to the second. They are stationary creatures that appear almost annually at the same place, and sometimes as early as April, depending on the year, and live until around the end of June. Compare Fig. 4, Table I. Way of life. Oil beetles are found on meadows, fields, mountain slopes, rocks, in open woodland, and also, rarely, in gardens. Their food consists of lower plants, particularly young, soft grasses, dandelions, violets, etc. Their movements are rather clumsy and awkward, yet they are capable of climbing plants with foot-high stems by gripping the plant with their feet while ascending. During the heat of midday, they hide from the sun in the grass. However, on cloudy days, One can also find them crawling and feeding during the midday hours. They consume their food with great avidity in the morning, and towards evening, often holding it steady with a forepaw, especially the shin bones, and frequently pausing during eating to stroke the feelers, and feeding organs from top to bottom with their forepaws. Upon contact, they retract their legs and feelers, exuding a sharp, corrosive yellow sap that quickly forms blisters on delicate skin and clothes, leaving difficult-to-remove stains, which is partly composed of cantharidin. Once the hole is fairly deep, it rounds it out through circular movements of its body, stopping occasionally to rest. If a large amount of earth has accumulated in front of the opening, the little creature often crawls out and distributes the soil on the sides to prevent it from caving in. The female lays its bright yellow eggs in a hole that is over an inch deep, which it digs with its forefeet into not too loose, but neither too firm earth, while pushing the excavated soil away with its hind legs and backside. Once the hole has reached the necessary size, the creature crawls out of it and sits down with its backside in the hole, so that only its head and forefeet, which rest like claws on the edge of the hole, are visible. In this position, and under alternating touch and feel movements, it lays its eggs in several batches. After doing so, it pushes the earth at the edge of the hole with its forepaws, and tries to gradually crawl out of the opening. Once it has emerged, it shovels soil onto the hole with its forepaws while pressing it with its hind legs and rear end until the hole is fully covered. During this very laborious task, it rests several times. As soon as it is done with its business, it quickly leaves this place and starts eating shortly after. By the way, it only lives a few days after laying its eggs. Here they wait, hidden among the anthers as mentioned earlier about the family, for a beat 27 to land on them, so they can cling to it and be carried into its nest. Others bore into the overlapping body segments, or even between the bee's neck rings with half or all of their bodies. The larvae of some species usually climb onto the bee's thorax, and hold on with their very sharp claws and spikes using the hairs and bristles there. 25, depending on the more or less favorable storage conditions, the eggs develop after 2,826 to 42 days, and the very active larvae crawl out of the ground and immediately embark on a social journey to various flowers, especially composites taraxicum, officinale, crucifers rapes, turnips, papilionacean chickweed, and labiate ajuga species. Geographical distribution and number of species. The latter often cause the death of the bee by irritating the particularly delicate wax apparatus. The genus Meloae is distributed in all parts of the world except Australia. In general, the way of life has already been mentioned in the description of the family, and the specific details will be given for the species concerned. 29. Spotted oil beetle. Meloae variegatus, Donovan. Europe counts 2,228 species with several varieties. Of these species, 13 are already found in Germany alone. Platine fig, 5 male, 5A. Tab, 39. Donovan, British insects, tab, 67. Mart, English entom. Fijarol, Valduaeon. 1. Leech, transact, of the Linn. Dow D. P. 37. Tab, P2. Fiji, 1, 2. Ebid, P. 243. Tatmanrar, Oring. Brandt and Ratzeburg, Medic. Zool, Dain, P. 17. Toward. Plate 16. On. Fiji, 6 female daughter. Brandt and Eriks. Monogur, General Mel. No L8, Act. Acad. Leopold. Dew. Carol. E. Nat. Kerr. Or. Tom 16. P. 128. Bud. Mello Majalis Fabricius. Cyst. E. Eluth. 2. Panzer's German Fauna, page 10, table 13. Olive insects, number 45, 6. On page 588, Systematic Entomology, page 259. Special Insect Book 1, page 327-2. Mantid Insect, page 215, excluding diagnoses and citations by Linnaeus. Table I, figures 4a, b and table 2, figure 4c. Meyer, Tentative Monograph of the Genus Mello, page 17, note 3. Latreille's General Catalogue of Crustacean and insect genera, page 218. Meloe secundus. Schaefer's icon table, figure 6. Poor figure. Meloe scabrosus. Marcham's British Entomology, volume I, page 483 and 5. Gyllenhaal's Swedish Insects, part 1, page 484. Meloe proscarabeus variant. I by Walkenaer, Fauna of Paris, volume 1, page 267. The larva description by Frisch. Beschreibung aller Insekten Deutschlands, volumes at 6, page 14, table 6. Characteristics: metallic green or blue, mixed with more or less purple, coarsely dotted and rugose. Elytra Holzschild transverse, slightly narrowed towards the rear with little raised edges. Wing covers wrinkled, dark green-black with a reddish shimmer streaked at the base. Abdominal rings above in the middle, metallic purplish blue. Length 5 to 12. Width 3.5 to 5. Later forms are currently unknown. The primitive larvae are 1.2, long, shining black with a blunt triangular head, otherwise corresponding to the characteristics given in the genus Meloe. Lifestyle. The beetle leads the lifestyle typical of the genus Meloe, as described for this genus. It is one of the most common oil beetles in most parts of Europe, next to the following species. The larvae appear in some years in incredible numbers, particularly on chamomile flowers, dandelion, and antijuga, and attack bees gathering honey and pollen from these flowers at a remarkable speed, including our honeybee in large quantities. They often bore so deeply that their entire body is hidden and irritate the delicate waxen membranes or ring membranes of the bee's head and thorax, causing it to die from strong contractions and pain. They do not attach themselves to the bee's hair like the larvae of other Meloa species, but rather penetrate with their body using the sharp upper jaws and foot claws between the scale-like overlapping segments of the abdominal rings and between theatropton, head, prothorax, and mesothorax rings. Bees cannot free themselves from these parasites, so they carry them back to their hives, where they can be found in large numbers on the bottom of the hive, on dead or dying bees, and in the hive debris, living and moving actively or dead and dried out in the crevices of the walls, and so on. Erz Eturi, Room 19, and in Bienenzeitung, Volume X, No. 8. Lastly, they all die, probably of hunger, because the bees do not allow them to enter their cells. Scarcely, however, for the reason that they only depend on the nests of Anthophorae as a place of residence where they undergo their further development, as Siebold states in Transactions of the Linnean Society Vol. A. See further under the mentioned species. Geographical distribution. For I have, for example, found 2 larvae of Meloe proscarabeus in the second transformation stage in a queenless colony that was almost entirely devoid of bees, which is a clear indication that Meloe larvae can live in the construction of honeybees, if given the opportunity. Apostatic significance. The beetle is distributed across all of Europe, Northwest Asia, and the Caucasus, but not everywhere to the same extent as, for example, in Germany. As is evident from the description of the lifestyle, the larva of this beetle, at least the primitive larva, is very harmful to bees, and perhaps the most dangerous known among all Meloe larvae. In some years when they appear in large numbers, bees are swarming around them, and one can see several dead bees circling around beehives, dying under the most horrible convulsions. And how many may not already have perished from their nectar? But not only working bees, but also queens are plagued by these creatures. I myself have only once had the opportunity to observe these Meloa larvae in my bees in the Smolensk governorate. They jump from the working bees, whom they, as mentioned earlier, import into the hives, onto the queens, and cause their death by drilling into their joints. In 1861, from the 5th in June, I noticed the busy workers of my 9 hives, which were standing in a circle on a meadow, affected by what is known as the disease of the tongue, or May disease. Individual bees fell from their hives, collapsed in front of them, and spun around on the ground in circles in pain, unable to fly again, though they did not die immediately. Instead, they lay before their hives overnight and died the following day. Many bees that returned from foraging also collapsed, exhausted, and died with convulsive movements. After picking up and examining some of these bees, I found, as described above, several, in some cases up to 18, mellolarvae between their abdominal rings, and even 2 larvae had penetrated into some of the rings. The number of bee deaths increased day by day, so that during the day, up to 200 bees lay dead or sick before each hive. By May 15th, in June, the mortality rates kept a consistent pace. From then on, deaths gradually decreased and stopped entirely by July 2nd. Queens were not harassed by mellolarvae, as happened with worker bees, but many drones were affected. They were indeed replaced by worker bees and died. Similarly, they affected young and even very young bees, just emerging from their cells, from the forager bees that brought in the larvae to the hive, causing their death. Inside the hive on the floor, there were also many dead and dying bees. Mellolarvae had mostly left them and hid among the debris. Some were scattered throughout the hive, but most escaped through the exit hole, and especially through the gaps in the hive. Of the forager bees, only those collecting honey usually died, fewer of those arriving with pollen. I could not definitively determine which plants the pollen-gathering bees brought the mellolarvae from, as the mellolarvae can be found on various flowers, and the bees also gather pollen from very different blooms. This was due to the fact that the larvae of Meloe variegatus in my area were particularly abundant on Ajuga genevensis, and the honey-gathering bees frequently visited the blooms of this plant that year, which is not usual because the nectaries of the nectaries, Ajuga, are deep, and the proboscis of our honeybees is relatively short compared to many other bees. However, I believe that the bees carried the larvae of Fragaria collina, from which they collected flower dust, and from which I reared several larvae of Meloe variegatus. The diseases and deaths of bees caused by these Meloe larvae were so similar to the symptoms of what is known as the toll disease, which is said to be caused by unknown factors and significantly reduces bee colonies in some regions and years, that I have no hesitation in identifying this disease with that brought on by the larvae of Meloe variegatus. Dzierzon believes that the toll disease is partly due to toxic honey that malicious beekeepers deliberately feed to the bees during raids. Something would, however, speak against this, namely that the greatest beekeeper of our time, the brilliant and keen-sighted Dzierzon, never observed mellolarvae in his bees, while he frequently encountered the toll or May disease of bees. 31. The disease has been observed by many beekeepers for a long time, 32, and described as more or less dangerous. However, even nature itself, according to his view, provides harmful plant juices, particularly towards the end of tree flowering, when the apple tree and the rowan tree are in bloom, causing many bees to die from this disease each year, especially young bees that have recently left their cells. However, as already mentioned, the actual cause could not be determined. It would indeed seem daring to me if I rejected Dzierzon's view and attributed the fatal disease to the larvae of Meloe variegatus donoff. Why shouldn't the Meloe larvae be the cause, especially since they bore so deeply into the bees that they go unnoticed and quickly leave the hive if present? Is there not enough keen-eyed observers to whom many important things escaped, which were later reported by those with less keenness? Are the meloid larvae, as one has seen above, not already known to have been observed on bees for a long time, but their great harmfulness remained unknown until 185,733. Of course not. It merely lacked careful observation. Should the meloid larvae have really only appeared harmful to bees in the year 1857, and exclusively with cup? Also, the season in which the disease occurs, namely May in warmer regions and June in colder ones, supports my view. The fact that young bees are often affected by the deadly disease further strengthens my view that the meloid larvae cause this disease, because young bees have a still very delicate skin, which the meloid larvae can easily irritate, while some older bees often escape without significant harm. At this time, one also finds the meloe larvae, which appear earlier in warmer regions and later in colder ones, but never after June, when the disease has not been observed. However, I do not want to attribute the origin of this disease solely to these insects, but it is likely that another animal, a specific endoparasite from the Gordiaceae order, namely Myrmis albicans zeb, and perhaps also Gordius subafurcus zeb, causes it. But I will discuss this further later on. Prevention. To protect bees from Meloe larvae attacks, it is essential that every beekeeper in their area focuses on eliminating oil insects. If a female of this beetle is killed, then he has simultaneously destroyed about 5,000 larvae, as the ovary contains approximately 5,000 eggs. Therefore, bees will continue to suffer more or less from Meloe larvae. However, it will be almost the same situation as with the May beetles. In Germany, millions of these are collected every year, and in some years without it being possible to completely eradicate them so far. Meloe proscarabeus, Linnae. Common cow beetle. When one sees bees infested with these insects arriving in their hives, the beekeeper should not fail to collect and remove the dead or dying bees, along with all the debris on the ground, in front of and inside the hive, and throw them into hot water or fire so that the Meloe larvae on the bees perish and do not spread to other bees in the hive. Table line. Fig 6. Male, 6AA, 6B. Linnae, Fauna Suecica, P227. N826, Cyst, Naturae, Data. P697. Part. Faber, Cyst.oe. Entom, P259. N1, Spec, Insect, Dory. P327. Cyst, Eleuther, D. P5087. Mantis, Insect, IP205. Part.war. Villers Entom, Die. IP397. Part. Gillen. Ins Suec. GLL. ITI. P2. P489. Marsham. Entom. Brit.war. IP481. N4. Olive. Turnu. Entom. 3. N455. Tab. I. Fig. IA. B. C. D. E. Brent U. Ratseb. Medic.war. Zool. P. 113. Figu. TFSTD. Bantoral. Or. 4. Male, 5 female. Brant U. Erics. Monagur. Generous Mel. Nod. Act. Acad.I. Leop.do. Carol.u. Nat Curious. Dora. Tom Seek.a. P. 113. Button. Meloe Atra. Meyer. Tentom. Monagur. Jenner. Mel.u. P15. Figior. VP3. 2. Cantharis proscarabeus varietas nigra, de Gier, insort. N1. Figior. 1. Ubers. V. Gutsa, BD, 5. P237. Meloe primus, chauffeur, icon. Tab the 3rd. Figioi. V. Abeld. U. Beschreib. Des Maiwurmkäfers Figure. I. 3rd. Meloe tecta, pans. Fawn. German.u. 10. Figior. 14. Crit. Duer. Tone. Revis the 1st. P140. The larve. Reomur. Mem. Fourth. Mem. Tuer. P490. Tab. 31. De Gier. Mem. V. Membo. 24. I. Tab. I. Zenker, Klopfleisch und Kirschner, Die Biene und die Bienenzucht, 1836, p. Tab 3. Fig 54. 1, 2. Poor figure. Von Sieb, Tarl. Stet, Entom. Zeit.gor. Yar G.1. 141. Page Yad. 130. Wing covers wrinkled in a sawtooth pattern. 6th and 7th antennal segments thickened in the male. Characteristic. Black-blue with a violet sheen, coarsely punctured head and neck shields, the latter almost square, narrowing slightly towards the back. Length 5 to 12. Width 2.7 to 5. Further forms are unknown. In the second form, it is 6 long, yellowish-white, otherwise completely matching the characteristics of the genus Meloe. The primitive larva is slightly smaller than that of the previous beetle, about only 1 long, with a more rounded, almost round head, yellowish-white or also more yellow in color, otherwise identical to that of the previous beetle. Habits. The habits of this beetle correspond to those of the previous one. He is the most villainous oil beetle across all of Europe. The larvae can be found on various flowers. I have observed them on rapeseed and turnips, where they lie in wait for bees to land, with the intention of mating. However, unlike the larvae of the previous beetle species, they do not bore into the joints, etc., of the bees, but instead cling to the hairs on the upper and lower parts of the bee's thorax. Once inside the hive, if not stopped by the bees, they enter cells, likely consuming a bee egg as is typical in anthophora nests, to other cells. For a single cell filled with bee bread cannot provide sufficient nutrition for their complete development. It was in the Moscow Governorate, near Podolsk. I was unable to observe the lifestyle of the larvae inside the beehives, and only once, while removing wax sheets from a nearly empty cluster hive with foul brood, did I find 2 second and star mellow larvae, each 6 lines long, that fell out of the cells. I am not even able to assert with certainty whether they were larvae of Meloe proscarabeus, as despite all efforts to raise them, they died after a few days. Larvae of Meloe proscarabeus in my hives, and never encountered any other species of Melo in that area. The fact that these Melale larvae could remain in the hive for such a long period, that they entered the second stage of life, is undoubtedly due to the fact that the bee colony was ill, and the few remaining bees did not pursue the Melale larvae. Food in one cell, it could immediately continue feeding in the adjacent cell. I cannot definitely answer whether these larvae would have gone through all stages if I had not cut out the comb building in which they were, but it seems almost certain that this could only happen if the primitive larva had just taken up residence on a comb where all the neighboring cells were filled with bee brood, so that when the larva consumed. For the larvae, in their second form, are not able to travel a greater distance on the vertically hanging combs and fall to the ground, where they are likely to perish. In my place, where the larvae were in a sugar glass, into which I had inserted a small comb with bee bread vertically, they attempted to climb it several times but consistently fell from the 5th cell. Eventually they crawled into the first row of cells, where they remained until their death. Geographical distribution and species number. This beetle has the same distribution as the previous one, but is much more common. Apostole significance. Order. They therefore do not bring about the bee's death, but they are still annoying, so beekeepers also seek to destroy this beetle. Diptera. The larvae of this Melo species do not harm the bees like those of the previous species, because they do not bore into the joints and wax-secreting apparatus, but instead, as mentioned above, cling to the hairs on the bee's thorax. Lin.Worm. Antliata. 2-winged. Fabricius.Dor. Family. Foridae. Latrile. Foridin. Latrile, his. Nature.Dor. Genere.1. Et partit.Dor. Des Crustak.Dor. Tom the 14th. Et ins. Page 394. Antennas, prominent, large, often flattened, bristly. Characterization. Small to medium-sized, very agile flies with a convex body shape similar to the genus Mordella. Head free, very short, flattened at the front, rarely as wide as the dorsal shield, with a broad forehead, very small face, large mouth opening, and a powerful, almost horn-like proboscis equipped with narrow suction surface. Sensilla closely set above the mouth edge, very short, 3-segmented, cylindrical. Third segment round, occasionally conical, with naked or finely hairy dorsal or terminal bristles. Eyes large, naked or finely haired. 3 ocelli present at the vertex. Scute mostly small, semi-moon shaped in outline. Dorsal shield slightly narrowed at the front, usually strong and often convex in shape. Wing large, lying flat and parallel to the body at rest, with a strong membrane, at the front edge 2 thick veins extending to the middle of the wing, from which 3 to 5 delicate branches sprout out and extend to the edge in various directions. The thick veins on the front edge correspond to the first and third longitudinal veins, the latter often divided. Below or before the fork, the first branch sprouts, which is considered a continuation of the first longitudinal vein. The basal cell is fused, but can still be perceived upon closer inspection, limited in the front by a thick vein that slopes down from the third longitudinal vein towards the inside, the small transverse vein. At the point where the small transverse vein branches off from the third longitudinal vein, the second delicate branch begins, corresponding to the fourth longitudinal vein. The following two branches correspond to the fifth and sixth veins. The anal opening is often completely absent. The legs are free, leaf-like, or kneaded. The scales merely suggested. Legs strong, with extended hips, broad, flat thighs, often slightly curved hind shanks, strongly elongated foot roots, delicate claws, and distinct pad-like structures. The posterior abdomen has 6 to 7 segments, usually somewhat short, wide in front, narrowing towards the rear, slightly convex downwards, sometimes indented in the middle. The ovipositors extend outward. Male reproductive parts protrude slightly, often cylindrical, and with a bump-like elevation or equipped with griffle-like organs on the belly. Rearwardly, they have curved support structures, and here, muricate teeth and 2 turbinate elevations at the anus. Larvae of many species are known. They are eucephalic, amphipneustic, leathery, muricate. Those of Phora incrustata can only be seen under a loop, white in color. Prothorax stigmata, represented by more or less long, fine, tubulose horns. The dolls are obtect pupae, more or less elliptical, crest at the ends, fringed on the sides and possibly toothed. The head and posterior region rounded and toothed. Many live alone, others in a social manner, often forming large swarms. Lifestyle. The flies are found on flowers, leaves of various plants, tree trunks, planks, and even on the windows of our apartment. Most of them prefer walking to flying, while others perform hour-long dances under tree canopies or near hedges and shrubs. The larvae live partly parasitically on various insects, their larvae and pupae, and partly on decaying vegetable matter, rotten potatoes, carrots, beetroot, and various mushrooms. Europe represents around 90 of the currently known species from various regions. Geographical distribution and species count. Exotic species are still very poorly known. Therefore, they are mostly beneficial insects, and only the larvae of Phora incrustata have been proven harmful through their parasitism on honeybee larvae. 34. Genus. Phora. Lati. Phora. Latrali. Hist. Nature.org. Genre. Et partit. Des. Crust. Bormund. Et ins. Tower. Tom. For 14th. p. 394. Characteristics. Mostly small flies with a humpback appearance and black dark brown or rust yellow coloration. Head depressed, half round, forehead long hairy. Last segment of the antenna round or rounded, large, with a naked or hairy erect dorsal comb. Ocellin standing in a triangle. Elytra strong, usually high-domed, without a transverse keel. Scutellum small. Middle tibiae mostly bare, or at most with individual hairs. Lifestyle. The flies are rarely found on flowers and trees, but mostly on the leaves of lower plants, planks, and windows in our apartments. They have a very short flight, and do not like to fly at all, but they move around with incredible speed. As for the lifestyle of the larvae, the same applies as was mentioned earlier about the entire family. Geographical distribution and species count. Throughout Europe in all countries, the number of known species is over 80, so the genus Phora includes by far the most species of the mentioned families. 35. Phora incrustata. Meigen. Plate I. Figs. 4-6. Meigen. Cyst. Data. Beerarb. Der Zweifel. Tund. Ins. Or. Tom. Vatju. Page.org. 212. Table 65. 5 door. Phytomines. Traps. Diptera. Suet. Page.yo. 6. Var. Dartwing. Mordellaria. Steiner. Fauna Austriae. Diptera. Page 338. Characteristics. Glossy black. Hind guat. Matte gray. First ring white. The cuts of the middle rings sometimes edged with yellowish brown. The head is black, with a prominent bump on the forehead. Eyes have very fine hairs. Palps, tentacles, and antennae are black or black-brown, with the last tentacle segment small. Wings are translucent with yellow bases, and the front edge has short comb-like structures. There are 4 longitudinal veins on the wing surface, with the upper ones highly curved, originating from the 3rd vein. They remain straight in their further course. Legs are jet black. A distinct wing fold extends from near the front edge of the 3rd longitudinal vein, almost resembling a 5th vein. The front legs, except for the base, shins, and foot pads, are rust yellow. The hind legs have inner comb-like structures, and the tip of the leg is equipped with a long bristle. The outer sides of the front legs have 2 to 4 strong bristles, while the middle and back legs each have 1. The hind legs sometimes have 2 bristles and additionally spurs. Length, 150 to 2 inches, width with spread wings, 2.8 to 3.8 inches. The larva fig. 4. Table 2 has 13 rings, is cylindrical, finely granulated, pointed at the front and broadened at the back, cut away obliquely, with a glossy white color and not very transparent. The prothoracic stigmata project, pyramidally, slightly downward. On each side of the prothoracic ring, there is a significant bristle. The head is very small, rounded, and can be retracted far enough that observing the larva with the naked eye would lead one to believe it acephalic, black in color, with short, fine 3-segmented antennae, whose terminal segment is spherical. Stigmites carriers are brown. Along the margin of the anus, there are 6 short flesh teeth, among which the second pair is the longest and equipped with fine brown hairs. Very close to the anus are 2 spherical projections. Length, 1.6 inches, width at the widest point at the last body ring, 0.6 inches, equipped with 4 teeth at the front head tip, and 1 tooth on each side of every ring. The 2 prothorax stigmas appear as 2 small, slightly sideways turned tubular horns. The pupa fig. 5 is on the back, with 8 rings at the bottom, elongated oval, both ends bluntly pointed, with a prominent toothed edge. Flattened on top of the rear side of the body, the front part inclined forward, uniformly and strongly curved below. Coloring is dirty yellow, somewhat transparent, so that after a few days the developed wings and legs of the nymph can be seen through it on the underside. Length 1.5, width at the widest point 0.39. Lifestyle, and some aspects of its development history. The fly, which is commonly found in most parts of Germany, Sweden, and Russia, throughout the summer and fall, more frequently in the latter. 36. Usually inhabits shrubs and boards. In Russia, in the governments of Moscow and Smolensk, I observed them quite frequently near beehives, crawling through the flight hole to lay their eggs in the bee brood. When laying her eggs, she always selects only the uncovered, but already quite mature brood, and lays only 1 egg in each bee larva. The egg is not as small as one would expect from such a small dipteron in general. She does this by inserting her ovipositor between the rings of the bee larva's body and piercing the very sensitive epidermis there, then depositing the egg just under the skin. Its length is 0.2, with a width of 0.1 at its broadest diameter. It is elongated oval, slightly broader, and rounded at one pole, and pointed at the other, with a yellowish-white coloration. The micropyle is located at the rounded end. It consists solely of a single eggshell. The egg does not lie in the bee larva vertically, as one would assume, but completely horizontally with the broader rounded pole, where the micropyle is located, pointing towards the head end of the larva. The vitelline membrane could not be found. The chorion is moderately thick, almost colorless, entirely smooth and transparent, allowing the yolk and embryo to shine through clearly. The embryos were already quite developed shortly after the egg was laid. 37, and lay in the egg with their hind ends slightly curved, while the front body was stretched out. The head end of the embryo could be distinctly perceived. The embryos filled almost the entire egg, leaving only a small space at the poles free. All eggs, by the way, still contained a considerable amount of yolk, which had a yellowish-white color and consisted of fat droplets of 0.05 and bubbles of 0.8. Fettkügelchen und Bläschen waren gelblich-weiß, Tor. Die Bläschen enthielten eine in Wasser feinkörnig gerinnbare Flüssigkeit, die spezifisch schwerer als das Wasser war, da sie stets untersank. Die Hautbedeckung der Embryonen war ziemlich undurchsichtig, weshalb ich den Darmkanal und so weiter tat. Von außen nicht beobachten konnte. Form, 3 Stunden nach dem Ablegen des Eis hatte der Embryo den ganzen Raum ausgefüllt und nahm eine gestreckte, dem Ei gleiche. Der Embryo war zum Schlüpfen reif. Zusammenziehen und wieder Ausdehnen der Körperschleife. Sehr bald bemerkte man auch stottrige Bewegungen mit dem gesamten Körper in Richtung des vorderen Endpoles, hervorgerufen durch. Die Bewegungen wiederholten sich ununterbrochen, unterbrochen nur durch sehr kurze Ruhepausen, dann aber immer kräftiger werdend. Nach 2 Stunden war die Eihülle am Mikropilpole mit dem Kopf der Larve durchstochen. As it bored, it left the eggshell behind. As soon as the tiny creature had freed its head from the eggshell, it began to bore itself vertically into the body of the bee larva, while most of its body was still inside the egg. 1 hour after piercing the front end of the egg, the entire larva's body had emerged, and had penetrated mainly into the fat of the bee larva. After hatching from the egg, the phorid larva was 0.1, longer than the egg, so it measured about 0.3 in mass. Its thickness, however, was slightly less than the diameter of the egg. Thus, the larva's length had increased at the expense of its thickness, possibly because the larva was contracted inside the egg. Their shape and coloring were the same immediately after leaving the ice, as I described in the adult larva, except that the skin was not muricated, but the spines were only suggested as very fine, slightly raised points. The phorid larvae burrow into the fat of the bee larvae, into which they had already penetrated at the beginning, as mentioned earlier, and establish their permanent residence until their complete growth. They grow extremely quickly. Already the next day after leaving the eggshell, their length was 6.5, with a thickness of 0.2. 48 hours after emerging from the egg, they shed their skin for the first time, and the very fine spines appeared with the new skin. 24 hours after the first shedding, the larvae gain a significant thickness, while their length remains the same. After another 24 hours, they are mature, and their length is now 1.6, with a thickness of 0.6. Now they shed for a third and final time. After 36 hours from the first shedding, calculated, they shed for a second time and growth doubles, so that 24 hours after the second shedding, they attain a length of 1.2 and a thickness of 0.4. About 12 hours after the last shedding, they change direction in the bee larva state, by turning their head end towards the posterior end of the bee larva. I have it in the Bee newspaper, volume 1860 N1. What motives may move the bee larva to take up a completely unnatural position is difficult to explain. The bee larva, which appears to be healthy, and at the same time reaches its growth alongside the phorid larva, even gets entangled, very soon also changes its position, and appears with its head end directed towards the bottom of the cell. However, not always are specific causes necessary. It is suggested that by the parasitism of the phorid larva, the bee larva feels pain, and probably curls up in all directions, and eventually takes a peculiar position within the cell as it dies. Nature has prescribed for it to prepare a protective blanket for its enemy. Why does the caterpillar of Pontia cratadigi, or Pieris brassicae, meticulously spin its enemy, who is taking its life, with the larva of Microgaster glomeratus emerging from it? About 12 hours after the phorid larva turns around, it leaves the bee larva, piercing its epidermis through the last body segment in the middle. Typically, once half of the phorid larva's body is embedded within the bee larva, it begins to pierce the brood cap in the middle with its head. Once it has pierced the cap, it falls down to the bottom of the hive and pupates here among the debris, or perhaps some part of the larvae crawls through the exit hole from the hive and pupates in the earth. Only in drone cells, where there is a greater distance between the bee larva and the cap of the brood, does the phorid larva first crawl completely out of the body of the bee larva and then pierce the cap, not in the middle, but rather on the side. Apistic significance. 12 days after pupation, the fully formed insect crawls out of the pupa through a dorsal longitudinal slit. This dipteron is the most dangerous parasite of bees, as it causes the worst bee disease, known as American foul brood, through parasitism of its larva. Indeed, when the phorid larvae have left the bee larva, it dies and transforms within the cell into a nearly homogeneous, viscous, sticky mass that has an unpleasant odor. Larvae have gone bad. Within a short time, not only is the entire brood of the originally infected hive dead, but neighboring hives are also affected and usually collapse. The miasma that spreads through the hive as a result of the decaying bee larvae also infects the other healthy bees, free from parasites, causing them to transform into the same sticky, putrid mass. The name fallbrood already suggests that it is a brood disease where the brood turns to rot. The parasitism of this fly in the bee brood is of such great importance to apiculture that I feel compelled here to delve more deeply into the topic of American fallbrood. Dr. Ahlefeldt was the first to distinguish between two types of fallbrood, dividing them into sporadic and epidemic fallbrood. This naming is too general and is often used by most beekeepers for any brood disease that causes the brood to simply die and turn to rot, much like a layperson might use the term nervous fever to describe various types of typhus. Non-contagious fallbrood is simply a freezing or starving of the brood. Ehrlich also classified them as non-contagious and contagious fallbrood, further subdividing the contagious type into good and bad according to Dzierzon. It can equally well be subject to cold, like the larva and nymph, as well as the bee egg, and even the perfect insect, just as the larva and the imago may starve. The frozen or starving brood likely turns into putrefaction over time, but the decomposition is quite different from what we experience with the decisive foul brood. The brood does not turn into a slimy mass, but retains its structure until the end, where it shrinks and dries out. 41. In most cases, a strong fuzzy fungal tissue also forms in some instances, under humid conditions a few days after freezing in the fat body of the body cavity, which finally breaks through the epidermis and resembles Botrytis bassiana, already observed by Professor Leichhardt. After this period, the larva or nymph becomes as hard as stone and dries up soon afterward. The same applies to the bee larvae that have died from hunger. Even more frequently than the mushroom mentioned earlier, a species of Isaria, as far as I could tell, Isaria flocosifraes, is found in dead bee larvae and pupae. However, this decay is limited to dead brood only. Live larvae and pupae are not infected. Therefore, this decay should not be considered a disease because putrefaction is a necessary process of every dead organic body. This is entirely different from the actual decay, the epidemic decay of Ahlefeldt, Ehrlich, and Dzierzon, which I would like to name Gangrena appum. The determined fallbrood, which I have just referred to as Gangrena appum, can be characterized as follows. Here, decomposition begins gradually within the living body of the larva, and reaches its peak after the death of the bee larva or pupa, and the decay process spreads from one infected larva or pupa to its neighbors. At the beginning of the disease, one finds in some or all of the covered brood cells, often at the front, but sometimes also in the middle. If you examine these fallen brood covers more closely, you will discover, with just the naked eye, a small round hole in the center, or somewhat on the side, whose diameter is hardly larger than 0.5. If you remove the cover from the cell, you usually find a mature, but not yet transformed bee larva, lying in reversed position, i.e., with its head end facing the bottom of the cell, and it has taken on a brown color. After 12 to 24 hours, or even after 36 hours, nothing of their form remains visible. If one crushes the larvae, one notices that their contents have transformed into a slimy homogeneous mass, with the odor of rotting horn or glue. They completely disintegrate into a slimy, sticky, homogeneous mass that smells strongly of bad glue, and which, after 5 to 7 days, often not until after 10 days, condenses into a dry, dark brown body that almost loses its unpleasant odor. Before the rotting bee larvae have turned into this dried-up mass, however, the healthy ones in the vicinity, surrounding the rotting brood, have also already entered the same state of decomposition. Occasionally, the larvae in some cells undergo transformation into nymphs, and bees also emerge from these. At least 90%, but as many as 95%, are affected by the epidemic. The evil now spreads ever wider, so that often within a few days the brood of an entire comb, measuring 8 inches high and 10 inches long, is affected by this process of decay, and eventually extends to the rest of the combs throughout the hive. When the disease has reached its peak in a hive, that is, when the greatest part, or at least half of the brood has turned to decay, one can detect a sticky odor even 20 steps away from the infected hive, as if one were standing in a glue factory, processing large quantities of horns and hooves into glue. In this way, not only can beehives in a city or village be infected and thus destroyed, but those of an entire district, or even a whole country, can become entirely devoid of bees within a short time. This pest does not only affect the originally infected colony, but also spreads to healthy neighboring colonies, so that in one summer all the colonies of a beekeeping operation can be destroyed, as almost all of the offspring from the colonies die. Once they begin to transform into nymphs and turn into the aforementioned matter. Once an outbreak occurs in a colony, it is usually spread to neighboring colonies by either the bees from the infected colony, or, more commonly, by healthy colony bees, who, feeling robust and strong, easily penetrate weakened sick colonies for honey collection, thus carrying the contagion over to the healthy colonies. However, the disease does not always progress as quickly and unfavorably as I have described. In some cases, the death of the bees proceeds slowly. Only part of the bee larvae enter a state of decomposition. The rest remain healthy, transform into nymphs, so that the colony still receives young bees, and often lasts for 2 or even 3 summers before finally collapsing. In the fall, the disease ceases as there is no brood present. But when spring approaches, and the brood begins to be produced again, it re-emerges with the new brood. In rare cases, the disease may gradually dissipate, and the colony can remain healthy. The behavior of bees in sick colonies varies depending on the severity of the disease. As a result, the bees mostly cease their work. However, as the disease progresses, a significant portion of the brood becomes damaged and takes on a mephitic odor. In the early stages of the illness, when only a small amount of brood has died, the bees are still active and vibrant, carrying out all their duties as they would in a completely healthy colony. There is little to no new wax production, and after foraging, only minimal flights occur. Similarly, there is little brood being laid. The bees work tirelessly day and night to ventilate the hive, trying to expel the contaminated air. Cells containing the dried-up brood mass are removed as much as possible, as it cannot be eliminated any other way. If the disease has spread even further, perhaps throughout half the hive, then all work by the bees stops entirely, at least within the hive, and no new brood is set. The bees restrict themselves to those parts of their nest that do not contain brood. If the disease reaches this state in spring or early summer, it often happens that the bees swarm out of their hive and take up residence elsewhere, only to re-establish themselves. However, they do not save themselves. As soon as any brood is laid and the bee larvae spin, the disease breaks out again. The former form, as Dzierzon 42 calls it, is the malign infective foul brood, while the latter is the benign infective foul brood. From my characterization of the epidemic American fall brood, it follows that 2 forms of this disease can be distinguished, one that brings about the ruin of a colony with alarming speed, and another that causes the colony to die slowly, damaging but not destroying the hive in some cases. Small and D. The malign infective foul brood, as described by Dzierzon AAO, corresponds to my observation and the above-mentioned characterization, although Dzierzon AO does not mention, nor does Skoltis 43, whether the concealed dead larvae were in an inverted position within the cells or not. The larvae that had turned foul also dried up to a crust at the bottom, which the bees could easily remove from the cells. Verlips 44 specifically state that all larvae which were brood foul, and lay with their head ends toward the bottom of the cell, just as I have described it now and observed it before, and in the Bee Journal, year 1860, number 1. However, Dzierzon's benign contagious brood fowl differs from mine in that Dzierzon mostly only observed it in uncovered larvae, which died and turned foul, while the covered larvae remained healthy and developed into complete insects. My benign contagious brood fowl, on the other hand, differs from the malicious type in nothing further than it gradually brought the colony closer to collapse, and in some cases disappeared by itself without destroying the entire colony. The majority of the larvae went into decay without shrinking into a dry mass that could be easily removed by the bees, but rather the dried mass adhered so strongly to the cell base and walls that when the bees tried to remove it, they were forced to break open the entire cell. Therefore, 3 types of American honeybee disease. I am omitting the non-contagious ones since, as I have shown, it is not actually a disease can be distinguished. 1. Aggressively contagious. Varieties. The good infectious lethargy that I have observed is only to be considered a milder form or modification of the malicious infectious lethargy, as it differs from the latter only in its lesser contagion, and probably does not develop into the malicious lethargy due to the lack of a greater disposition in the bee larvae to absorb the contagium. Therefore, I believe it is more appropriate to classify the lethargy not according to the extent of its spread, but rather by the age of the bees affected and the symptoms as the disease progressed. And 2. A lethargy that usually only affects the uncovered bee larvae, spreads slowly in the hive and sometimes disappears by itself, without destroying the hive. In this way, one would have a lethargy that mostly affects the capped, nymph-like bee larvae, spreads rapidly throughout the colony, and completely destroys it. Furthermore, a silly modification of the former lethargy, which, like this, mostly only destroys the covered larvae close to transformation into nymphs, but spreads slowly in the hive and sometimes disappears by itself, without preparing the hive's demise. Because they contain the contagion, or due to the residue of dried brood mass left in the cells that is not removable by disinfecting agents. All forms of American foul brood, whether malignant or benign, cause significant losses to beekeepers, not only by reducing a large portion of the brood, and thus often leading to the collapse of the colony in the most frequent cases, but also because the beekeeper cannot use the valuable wax cells after the demise of a foul brood-infected colony. It is not possible to completely remove the varroa mite from the cells, which therefore renders the frames unusable and forces beekeepers to melt down the wax, at least from those frames containing brood, which constitute by far the largest part. However, every rational beekeeper knows the high value of empty wax combs for them. Similarly, bee colonies that had varroa-infested colonies in them are, according to Dzierzon and several other beekeepers, not usable for new colonies 2 or 3 years later, as they would otherwise produce varroa mites. Even the place where formerly unproductive combs stood cannot be used a few years later, according to von Berlepsch, because the site has the property of infecting healthy combs for longer than a year. The same applies to honey from varroa-infested hives. Honey from such bees should not be used to feed healthy bees, even though it does not harm the insect completely. It is clearly proven that brood becomes infected with varroa after consuming such honey.u. Similarly, bees from an unproductive comb cannot be used to strengthen other healthy combs, as they carry the contagion. Based on my observations, indeed only after 2 attempts, the queen also infects the healthy combs. According to Dzierzon, von Berlepsch, Kleine, and many other beekeepers, nothing from an unproductive comb should be used for other healthy combs, except the queen, who should not spread the contagion further. The cause and cure of this disease have therefore always been a matter of lively interest to beekeepers of all nations who keep bees. From what has been said above, it becomes clear how destructive the fall-brood American bee disease is to bees, and how harmful it is to beekeepers, and in a national economic sense. Junius Moderatus Columella. It is no wonder that we have abundant material on the causes and treatment of this malady. 47 already mentions this disease of bee colonies, which he calls phagedena in Greek, and gives means for treating a colony with queenless bees. According to him, this disease arises from loss of bees, caused when they are suddenly caught in rain or storm while foraging and perish. As a result, the wax structure is partly stripped of bees and begins to rot. Similarly, honey stored within also spoils. He recommends combining such a colony with another to replace the lost bees. Plinius 48 believed that in the combs a growth clavis formed, which was a deformity of the bees. The most common view on the cause of American foul brood was, and still is, among most beekeepers, as mentioned by Columella, namely, due to sudden large losses in the colony, a part of the brood remains unattended and unaffected by heat from the bees, dies off, and ultimately turns into foul brood. Or even without any loss of the colony, but with cold weather forcing the bees to retreat to the center of the hive, the outer brood cools down, and eventually also turns foul. The second most common view on the cause of American foul brood is feeding the bees with American or Polish honey, or even German honey that has gone fermented. Dzierzon also believed that American honey caused foul brood. He himself is believed to have lost several hundred of his combs through feeding them with this honey. 49, according to less common theories, the origin of this disease was attributed to toxic honey, flower nectar, which bees collect from their forage. Furthermore, it was thought that the American foul brood could be caused by the beekeeper himself if he suffered from spoiled juices, such as scrofulosis and even worse diseases. Finally, in recent times, street dust entering the brood cells has even been considered a cause of the death and slow decomposition of bee larvae. It was also presumed that a mold, Mucor melitophorus, found in the chylous stomach of bees, negatively affects their food preparation, resulting in undigested feed for the brood, thus making this mold an indirect cause of foul brood. Feeding bees with American or Polish honey can cause this disease only if these honey types come from colonies affected by brood disease, or if they contain a mixture of honey from sick colonies. The view that the disease known as American or Polish honey causes the sudden loss of bees and subsequent chilling, freezing, or starvation of the brood can only apply to what is known as non-contagious brood disease, ELI, the liquid bodies from the solid parts. This practice, unfortunately, is very common in countries like Russia and North America, where beekeepers in the fall use sulfur to smoke out their hives for honey collection, mixing honey, bee-bred pollen, wax, brood, and even bees from healthy and diseased colonies into a paste-like substance through which they filter the honey, or more accurate, such honey served to bees or even accidentally tasted by them must necessarily produce the disease. But this would only be considered as a secondary cause of American foul brood. Sour or fermented honey, if it does not come from diseased colonies, does no harm to the bees, at least it does not cause American foul brood. Dzierzon also states somewhere that sour honey does no harm to bees. Attributing the origin of American foul brood to so-called toxic or trapped honey, as some do, seems a bit far-fetched. I have often intentionally added ferment to honey, allowed it to sour, and fed it very strongly acidic to the bees without noting any harm, let alone American foul brood. Only one hive will utilize this nectar, but all the hives simultaneously. Humans who handle bees. For if the bees were to truly carry toxic honey and the like, then the disease would need to recur more frequently. It wouldn't be just one hive in a bee colony becoming sick, but rather, or very soon after, several or all of the hives in the entire colony would fall ill. For it is known that when there is abundant nectar, especially honeydew, not even more far-fetched is the idea that the disease, foul brood, originates from the exhalations of sick scrophulus, etc. Such a theory does not require commentary. It follows logically. Healthy, non-infested colonies of bees often bear this fungus, while those with American foul brood rarely, if ever, harbor any fungi. I have observed this in my hives in Moscow and Smolensk on numerous occasions. As for the thread fungus, which is said to cause a disruption in the production of digestive juices in the chylous stomach, and thereby, as mentioned above, indirectly induce the disease known as American foul brood. It is impossible to accept this forebrood. Several reasons. At least the bees in all of my colonies were free from fungi. Similarly, honey containing green-spotted pollen cannot induce the actual disease. As one can see, the views mentioned here about the origin of American foul brood are of a very problematic nature and rest on mere and quite untenable hypotheses. With regard to the proposed cause of American foul brood from street dust, it is necessary for such a large quantity of dust to penetrate the brood cells that it completely blocks the stigmas and pores of the bee larvae, leading to their suffocation, but this does not constitute American foul brood. Having, however, rejected all the beekeepers' views on the origin of American foul brood, the question will be asked of me, then from what does American foul brood actually originate? This question I have already answered in the description of the life history of Phora incrustata. This dipteron is the real cause of American foul brood. The parasitism of this fly is a larva in bee larvae. I observed for the first time in 1859 at Podolsk, near Moscow, and described in the Bee Journal of 1860, No. 1, p. 11. One might perhaps object and say, should foul brood really be caused by the parasitism of a fly? Should it not rather be the other way around? That is foul brood not the cause of the fly's parasitism? Does the fly perhaps lay its eggs only after the larvae have already died? This I absolutely deny, based on my observations. One can very easily convince oneself of the presence of small phorid larvae in the still uncovered living larvae by choosing those larvae from near the fulterus for examination. Cut off the head of these larvae and press out their contents cautiously. With many larvae examined, one will dislodge the parasite from some or others. Using a rather powerful magnifying glass is safer than choose those larvae that show a fine scar between any ringlet pair. The scar comes from the fly's egg-laying tube, which bored into the bee larva. With practice, one can even extract the fly egg from the bee larva. The egg, as mentioned earlier, lies just beneath the skin of the bee larva. The emerged phorid larvae immediately bore deeper into the bee larvae, as previously indicated, and make their home in the fat networks. After 5 days, the phorid larvae have grown up, and this regularly occurs at a time when the bee larva is already cocooned and awaiting transformation into a nymph. Only very rarely did I encounter phorid larvae in already transformed bee larvae into nymphs. Once the phorid larva has reached adulthood, it leaves the bee larva as described above, to pupate in the hive debris or in the ground, and only now does the bee larva start to rot. However, this does not happen immediately. On the first day, the bee larva is still completely fresh, and one can only recognize a very fine opening at its rear end, through which the ferret larva crawled out. The opening was originally larger, but soon after the ferret larva emerged, it appears very small, yet clearly visible with the naked eye. By the following day, one notices that the walls of the bee larva's body have turned darker and yellow at the wound site, almost brown by the 3rd day, and have extended to almost the 4th ring. On the 4th day, the bee larva turns browner up to the 7th ring, and the hindmost body rings are usually already dissolved into a viscous, sticky fluid. By the 5th day, the rest of the larva turns brown, and half of it has dissolved. On the 6th day, the entire larva transforms into a homogeneous, sticky, and as mentioned earlier, lemony-scented mass. The dried mass typically fills about 1/4 of the cell. In this state, the mass remains for 5 more days, after which it gradually becomes thicker until, after another 5 days, it hardens and dries to a dark brown mass on the floor and cell walls. There is no sign of mold formation. Under the microscope, the putrefying mass appears striped in waves, with occasional round granules observed that consist of undigested pollen, or, more accurately, cellulose. The putrid mass does not float on water, but sinks to the bottom, thus being specifically heavier than water. If one adds an amount of cold distilled water equal to twice the mass of the putrefying matter, only a very small part of the mass will dissolve, and the water will take on a brown-red tint. A 4 to 10-fold amount of water could only slightly dissolve more of the mass. Upon careful evaporation in moderately heated sand, the dissolution took on a syrup-like consistency of brown color, and tasted slightly sweet with a bitter aftertaste. It consisted of extractive substances and a little grape sugar. In stark contrast, hot water had a vastly different effect on the putrid mass. Twice the weight of hot water infused into the mass virtually dissolved 1/4 of it. Furthermore, pouring 4 times the weight of hot water over the mass and leaving it in the heat for 12 hours even dissolved more than half of the brood mass. The filtered solution was yellowish-brown and congealed into a thin, sticky, transparent gel upon cooling. In cold water, this gel dissolved in every ratio. When a portion of the solution was transferred with alcohol, a fibrous white precipitate formed. When exposed to air, the gel deteriorated within 48 hours at 18 C and showed an acidic reaction. Similarly, when the solution was mixed with a small amount of pyrogallic acid, a white precipitate appeared that solidified as a rather viscous, sticky mass at the bottom of the container. Ether, alcohol, and benzol did not dissolve any of the gel, while sulfuric acid, salt, and acetic acid had a completely dissolving effect on it. Upon evaporation and subsequent cooling, the liquid solidified into a complete glue-like mass. The solid bodies remaining in the filter after the putrid mass of the brood recognized the larval skin clearly. Alcohol, dissolved in heat during a 24-hour digestion, slightly separated some of the mass and turned brown-yellow. Based on these chemical examinations, I believe that the fluid extracted from the putrefied mass with hot water consists of gluten. An eighth quantity of cold water caused a yellowish, powdery precipitate, which consisted of a resin that burned with a bright hissing flame when ignited. The mass consisted of chitin. The resin was soluble in ether and benzene. Ether and benzene had no effect on the insoluble mass drawn out with alcohol, nor did diluted acetic acid or potassium lye, even in cold. After dry distillation, the putrid mass yielded the following results. 10 drachmas of carefully removed putrid brood mass were placed in a small glass retort and subjected to distillation in a sand bath with an initial very gentle spirit flame. First, as expected, water ran over. After 1 drachma of water had passed, the overdistilled liquid showed a weak alkaline reaction. The container was immediately changed. It was fractionated again. It may have been approximately another drachma of alkaline water that passed over, as white solid leaves were seen going with the liquid, which ceased very quickly. Now stronger, alkaline reacting water ran over, along with very little brown empirical oil, which floated on top of the water. Shortly thereafter, carbonic ammonia in small quantities began to deposit on the sides of the retort neck. After distilling the whole half an ounce of liquid, a dark brown oil appeared with little alkaline water, which sank into the water. In the retort, a highly glossy and very hard coal remained. The alkaline water contained ammonia. The distillation was continued until dry, and in total, 5 1/2 drachmas of liquid and 15 grains of solid distillation products ran over. The oils seemed similar to those obtained from the dry distillation of bones. The same results were obtained from tests on the already dried raw material. The salt accumulated in the retort's neck, as mentioned, was ammonium carbonate. The solid white bodies that passed into the water immediately consisted of pure but flammable wax 50, which later turned brown through oxygen uptake from the air. However, it was not subjected to dry distillation. Now I cannot keep silent about one circumstance. Not all larvae of rotten bees contained the above parasite. Many, indeed, even the greatest part of the larvae of rotten bees, had no opening in the fallen cover, and it could not be proven that a parasite had been present in them. From the intestinal canal the fire spread to all sides of the body. The decomposition of the larvae did not begin, as in those that harbored the parasites, in the last body rings of the organism, but the fire, as I call the disease, started in the intestinal canal, which became strongly brown and almost black in a few days. On the 4th day the entire fat substance and the tracheal system are usually already in decomposition, and the stigmas are clearly marked by a brown coloring that indicates the fire. Parasite. On the 5th day, the viscous contents from the intestine flow into the cell, through the mouth opening of the larvae, which, with their head end directed towards the cellular bottom, we have observed in those bee larvae infested by the parasite, as they penetrate the cell. Unavoidably, the question arises as to what these bee larvae may have suffered from in the foul brood, since they were entirely free from parasites. Now decomposition proceeds rapidly. On the 6th or 7th day, the larval skin bursts open on one side of the body, and the entire larva is engulfed by the slimy, viscous fluid that has already been mentioned, which, whether observed under a microscope or chemically analyzed, differs in no way from the mass of those bee larvae abandoned by the PA. Certainly it was only due to the miasma that arose from the originally dead and eventually decaying bee larvae infected by phorid larvae in the hive. If one considers how a mere few hundred foul-brood bees in the hive spread a mephitic odor, then the disease of healthy larvae from such inhaled gases appears perfectly explicable. But the contagion does not even need to be transmitted through the harmful gases that the bee larvae inhale. The worker bees, which care for both the sick and healthy larvae, are themselves the medium by which the contagion can be transferred from the sick larvae to the healthy ones, and necessarily so. In the pest, Asian cholera and typhus, people often live with and in the same room as a sick or deceased individual without contracting the disease. The same applies to bee brood. Not every larvae is susceptible to the disease. However, not every larva in the diseased hive is infected and dies, but some, as mentioned above, can develop into fully formed insects while still in the diseased state, which may find its explanation in the analogy that we see this even in the most contagious human diseases, such as prophylaxis. Preventive measures are very difficult to implement. The worker bees do not seem to seriously hunt them either. It is impossible to prevent flies from entering the hives. I have frequently observed flies moving freely in and on the walls and combs of the hives, sometimes even crossing an entire cluster of bees. They may also be pursued by the bees, but the bees do not handle them as they usually do with other insects, instead turning away. Even when pursuing ants, they show a certain respect or aversion. By the way, the phorid is so agile that it only rarely succeeds in getting between the bees' mandibles. It is advisable for beekeepers to catch these flies from near their hives, as the little creature is often overlooked due to its size and unremarkable coloring, and it is also so quick that it would be difficult to capture. This must be done immediately at the beginning of the disease. By cutting out the bee brood, the brood of the phorid is also removed, preventing the fly's reproduction and setting a goal to curb the disease. However, if the pestilent brood breaks out in a hive, there is only one means of preventing its decline: remove the decaying brood, or more securely, the entire covered or nearly covered brood, and replace the removed brood frames with empty wax frames. I recommend carrying out the destruction of the bee colony in the following manner, as I have done with my colonies in recent times. The interaction of sulfuric acid with the mixture of manganese hyperoxide and salt produces chlorine gas, which kills the bees. If the evil has reached a greater dimension, and the influence extends to healthy bee larvae, then the remedy is applied too late, and the entire colony, including its hive and construction, must be removed and destroyed to prevent other healthy colonies from becoming infected. Take a part of powdered manganese hyperoxide brown stone, 4 parts salt. Mix both ingredients thoroughly together. Place them in an earthen vessel on the bottom of the hive and pour over it 2 parts, or even more. This is not so precise. Commercially bought sulfuric acid, and immediately close the hive. The dead bees are removed from the hive and buried in the ground. The brood is cut out of the combs, and to prevent the loss of wax, the brood combs are melted. The structure is kept sealed for 2 days. The honeycombs and the empty wax tablets are then hung back up in the buildings and develop a significant amount of chlorine gas once more following the specified method, namely by taking 2 ounces of manganese peroxide, 8 ounces of salt, 4 to 6 ounces of sulfuric acid. After this period, based on my experience, the wax and honey tablets can be safely given to others or used for settling purposes. The chlorine gas, if developed in sufficient quantities, destroys any miasma. At least, the author has been able to use wax and honeycombs without damage, as well as the structure. If all the sticks are infested with the disease, however, it is very serious. They will likely lose them all and have to start over by purchasing new bees. By the way, a rational beekeeper will not let things get that far, but if a colony is affected by this disease, he will remove it in the specified manner beforehand. Most beekeepers, even the greatest authorities like Dzierzon, von Berlepsch, and Kleine, advise catching queens from diseased colonies and using them to establish new colonies, stating that queens do not carry the disease over. The author has made 2 attempts with queens from diseased colonies and found that, like working bees, the queens propagate the contagion. Family: Brawlina, Egger, Apis lice, Plate 2. Figs, 7-8a Dartmoor, Egger in Verhandel, Des Sewell, Botan ... Verines in Willen, Tom. 3, Iron. Page E. 401. Characteristics: a family of wingless dipterans represented to date by only 1 genus and species, similar to the hippobosids and Nycterbinidae. Standing vertically separated from the back shield, very large, nearly as wide as the thorax, triangular, convex in front, flat at the back without eyes or ocelli. Palps short, bulbous, surrounded by the cheek flaps. Snout short, scaly, hollow, equipped with 2 thin elliptical plates lying vertically side by side. Lower lip unsegmented. Wings and tails absent. Antennae short, sunk deeply into the frontal sinuses, three-segmented, with a rounded terminal segment and feathered dorsal cones. Breast rings fused into a common chest box, half as long as the head, ring-shaped, slightly expanded towards the rear, furnished on each side with a large stigma. Legs inserted near the midline of the underside of the chest box, short, of equal length, with thick, flattened shins, slightly curved tibiae and 5-segmented feet. The abdomen is highly arched, oval in circumference, 5-ringed, and densely bristled. Anatomically, at least regarding the female genitals, the Brawlina resemble Hippobosidae closely. The 4 root segments are short and cross. The terminal segment is quadrangular. The claws consist of 30 to 32, bristly and comb-like, movable teeth located at the front edge of the terminal segment. The hooklets have thin stems, bulbous. The ovaries here also form 2 oval sacs from which the oviducts lead via a short oviduct into a spacious, almost heart-shaped sac uterus. The receptacle for semen appears to be absent, at least I have never been able to locate it. There is a secretory gland with numerous tree-like branches. In both ovaries, only 4 embryos are found in their entirety, which, each individually, complete their development into adult larvae in the uterus, and the larvae live on the juice separated by the secretory gland. When the larva is mature in utero, the Brawla sheds it, or rather, simply lets it fall and leaves it to chance. On the same day they are laid, their skin hardens, forming an oval-ton pupa consisting of 11 fine rings and acquiring a initially dirty yellowish, later a darker, almost brown color. The larvae figged. 7. Table 2 are 0.5 long spiraled, though only visible under a microscope, entirely smooth, white acephalous, that is, equipped with 2 extremely small, angular depressions, thus metapneustic. Genus, Brawla. Niche. Bees lie niche. Valdethevere. Niche, the families and genera of the insect animal, in Germar's and Zinken's Summer Magazine for Entomology. 1818. p. 286, 314. Character of the family. Brawla coeca. Niche. Bonwell. Blind bees lie. Niche, the family and genus, etc., in Zinken's Magazine for Entomology. Balder III, 1818. Totaro. p. 286, 314. Valdali. Reaumur. Memoirs on Serving the History of Natural History of Insects. VP 717. Tab 38. Darif. Figuar. 1-3. Costa. Proceedings of the Royal Institute. Voldi Ur. 1845. Entomobia Apamdo. Balder III. Egger. Contributions to a Better Knowledge of Brawla coeca, Niche Proceedings of the Zoological and Botanical Society in Vienna. p. 401. F.1. Scheiner, Fauna Austriaca, Diptera, p. 650. Characterization. Horn-like, shiny brown-red, feelers yellow, bristles and hairs black. Length 0.2 to 0.3 inches. Lifestyle. The perfect insect is an ectoparasite that constantly lives on bees and feeds on their juices. On the bee, the little creature moves with great certainty, runs around on it very nimbly, but only forward, while other pupae can also move backward, and does not fall off even during the bee's flight. Its actual resting place on the bee is the back shield. In the hive, where bees often cling together in a chain-like formation, it sometimes changes its host by crawling from one bee's leg to another, and then settling on the thorax. Without the bee, these insects are unable to move properly and die within a few hours. Once arrived, it presses its feet tightly together, uses its combs to get into the very dense hair of the bee, which it parts, and then quickly reaches the back shield, where it attaches itself with its hollow snout, and often remains immobile for hours, sometimes even days. Sometimes, however, one encounters these little creatures, even when the bees are crawling around in the hive, in a swaying position, where they hold on to the bee's thorax with their middle and hind legs, while their front legs comb the bee's hair aside. If playing, only the young individuals that have emerged from the pupae possess some vitality and survive for up to 96 hours due to residual nutrients stored in their bodies from the pupils. They infest all 3 types of bee individuals. Bee lice usually appear singly, but often in very large numbers, sometimes over 100 on a single bee. However, they should primarily infest and show a special preference for the queens, so that, if one cleans the queen of them, the queen is quickly reinfested with these epizoans. In some years, these animals are very frequent in several hives, without distinction between weak or strong ones, to such an extent that almost every working bee has a bean louse on it. 53. By autumn, most of them disappeared, but a few remain to this day, November, and will probably overwinter with the bees. Yes, some working bees are teeming with them in the same quantity as the queens. 54. This summer, 1864. My Italian bees in Leipzig were also plagued by these animals, but I have not seen the queen infested with lice, and also some drones. The reproduction of bee lice likely occurs on the bees themselves, as these small creatures, when removed from the bees, move very clumsily. However, I have not been able to observe the act of reproduction. 55. The lifestyle of the larvae has already been discussed. In the first 2 days, the creature is straw yellow and has a soft skin filament. Only on the 3rd day does the skin harden and turn brown. Geographical distribution. When the mature insect leaves the pupal case, which happens 13 days after pupation, it sits still on the bottom of the hive and waits for a flower, like the meloid larvae, if a bee comes near, which then quickly grabs it by the legs and carries it to the back shield of the bee in the described manner. The bee louse seems to be more prevalent in Western Europe. It can be found throughout Germany, France, and Italy. In Russia, with the exception of the Baltic provinces where I have observed them, they seem to be absent. At least, I have never encountered these bees in Russia, despite once owning a fairly large beehive, and they are completely unknown to beekeepers there in the various governorates I have visited, both northern, central, and southern. Apistus significance. Generally, these epizoans do not cause much harm to bees because they usually occur only sporadically. However, if they are present in larger numbers in a hive, such that there are hardly any bees without some form of louse infestation, or when several bee lice occupy a single bee, and especially the queen, then this causes a loss for the beekeeper. The bees infested with lice appear dull, and are sluggish in their work. This I observed particularly in my Italian bees. This spring 1864 and may probably die earlier than usual from the loss of their juices absorbed by the parasites. Prevention. The queens heavily infested with these parasites always look emaciated and die in winter, which naturally leads to the colony's decline if one does not have access to another queen to replace her in spring. The method suggested by Edgar 57 for preventing the further spread of lice among bees involves brushing off the lice with a feather flag from the bees. However, this can only be effective when, for example, only the queen or a small number of worker bees are infested. But if the lice are widespread in the colony, as is often the case, according to Bose in the year 1858 AAAO, where every bee was infested, this method would likely be impractical, since the bee lice, as mentioned above, lay their larvae on the bottom of the hive. The most practical approach is to clean out the hives as frequently as possible, thereby removing the brood larvae with it. Vermeer. In particular, one must also thoroughly clean the crevices, etc. Vermeers. Classat. Nemathelminthus. Vogue tar. Runvermeer. Jew unwell. Nematoid dia Rudolphi. Seitenvermeer. Gordiaceae von Siebold. 58 family. Characteristic. Thread-like worms, sometimes with papillae, with a mouth and intestine replacing structures, permeating the entire body cavity with a cell body without an anus. Dizing. Gordiidea. Gordian. Dizing revision of nematodes. Mathematical and Natural Sciences class taught. Proceedings of the Imperial Academy of Sciences in Vienna. Volvo 42. Katnur. p. 599. Males glossy and darker. Characteristic. Very thin worms of varying length, from 1 to about 4, generally of brown color, sometimes appearing dark or light, often yellow. Head without papilla. Oesophagus short, opening into the cellular body parenchyma. Male tail forked. Genital opening located at the point of division, equipped with spines but no spicula. Female genital opening at the tip of the tail. Young possess a tubular body showing a distinct tail portion, fore part of the body armed with hooks. During mating, the male winds his rear end spirally around the female's rear end for an extended period. After reaching sexual maturity, they bore through the skin of their bodies again to emerge outside, where they live in water, mate, and lay eggs. Habits. Gordian worms are endopterous, which bore into various insects of all orders, as well as arachnids and snails in their youth, encapsulate themselves there, and later nourish on the fat substance of the host's body, undergo metamorphosis, gradually attain sexual maturity. The eggs are not laid individually, but are connected by a slimy mass that hardens later, forming a spiral wound string that looks like a thicker, round lump, which can be unwound again. Genus. Sectorized the existing ones, so that at present only 11 species are accepted with certainty. The total amount of egg strings laid by some large females can exceed 8 feet and is either deposited on the water floor or attached to plant stems, etc. Geographical distribution and number of species, the Gordians, being parasites of insects in general, are found worldwide alongside these insects. Dysing counts in his Systema Helmenthum 118 species, which he however distinguishes almost only according to the hosts in which they are found, which, however, according to Siebold 60, are to be considered as very doubtful species, and Dysing later incorporated most of his former species in his revision of Nematodes 61, and more accurately Carrot. Gordius. Linnae. Cyton worm. Linnae. Systema Naturae. ed. D. Du 2. I2 p. 1075. Character of the family. Gordius subaphurcus. B. Siebold. Tab 3. Fig. 2. Male, 4 female, by Siebold, Stettin, Entom, Zeit.O. Jurg, Thou, Einworm, P296, Dysing, Cyst.wo, Helminth, Bolguer, 2, P90, Meissner, Beiträgie zur Anat, Punt, U. Physiol, der Gordiation Zeitschrift für Wissenschaft.ur, Doddle BDA, Heft 1, U2, P59, Ibid, Tab 3, to VI, Addendum by Siebold, P143, to Cyr, Darrell Dow, Gordius Tolosanus, du Jardin, Analyse des sciences naturelles, Tom de Titoto, page.war, 146, Dysing, Cyst, Helminth, Vol. Duo, Tadamon Oral, Hunded, page.war, Male tail, table thread, 106, Doroi. Characteristic. Brownish, gradually and distinctly tapered towards the front. Head continuously tapering, becoming gradually invisible, slightly truncated. Female tail table thread. Length, 1 to 1. Fig. 2 bent downward at the base. The genital opening located in the fork of the abdomen, preceded by small spines arranged in several rows in a curved manner. 4 sharply rounded, divided into 2 short branched forks by a shallow longitudinal groove. The genital opening lying in the fork. In youth, these worms have a cylindrical body divided into a thicker frontal head and a thinner posterior tail part. Compared to table thread, the head part possesses a retractable proboscis around which 6 hooks group. Additionally, there are still 6 larger hooks located deeper. Fijiwo, Kanran O. 1. Lifestyle. What was mentioned about the genus also applies here. In any case, the presence of a Gordius on a male bee is very peculiar. The Gordius subaphurcus occurs in various insects. I once encountered an example of this animal, 3 inches long, when accidentally crushing a drone in July. If it had been a worker bee hosting this creature, that would not be unusual. However, the occurrence in drones, which leave the nest only to fly around in the air, is paradoxical at least. In the drone, the animal could have only entered through a passive wandering. Worker bees often sit near water, and even on objects barely protruding from or wet with water, such as straws, pipes, etc., to collect water, where it's possible that a young Gordius larva could invade. Another animal, for example, as many other endopterites tend to do, then certainly pierce the intestinal wall to reach the fat tissue. However, they can passively enter the drones if, for example, they do not undertake a second active invasion, as I believe, because I found Gordiacean worms in the drones that give them no opportunity for invasion. I therefore believe that the Gordians, and also the Myrmidon, which I found in large numbers inside the drones, see below under the relevant worm, before they grow into sexually mature individuals, do not remain with the first invasion, but leave the first host where they had insisted Gordius to later move with the animal's food into the gut of a family. Myrmidea. The working bees, with the water they suck up, also provide young Gordians, which are indeed only 160 long and 1120 thick with nourishment. Through the working bees that supply the brood and trained drones with food, the drones can receive endoparasites, either as larvae or as fully developed insects through the food given off by the worker bees regurgitated. Dizing. Myrmidon. Dizing revision of nematodes. Proceedings of the Imperial Academy of Sciences in Vienna, Mathematical Natural Sciences Class, Volume 42, Donor, P605. War. Characteristics. Very thin, up to 5 inches long worms of a white color. Head covered with papilla. Oesophagus long and narrow, embedded in the cellular body parenchyma. Tail tip intact, with several rows of papilla and 2 spicula. Female reproductive opening, located in the middle of the organism. The embryos resemble perfect worms, possess no hook-armed structures like the Gordians. The eggs are laid individually, either simply or enclosed in a capsule, and then provided with a chalice at each pole. Lifestyle. Myrmidons lead an endoparasitic life, like the Gordians and various insects, at all stages of their development, boring into them as juveniles, earth where they molt. After molting, they become sexually mature, mate, and lay eggs. They sometimes emerge from the insects in such great numbers that they cover parts of the earth and give the appearance of having rained down from heaven. 63 as mentioned above. The eggs are laid individually, not in water like those of the previous family, but in the earth. Geographical distribution and number of species. As the Gordians, the Myrmidon are distributed throughout the world. However, their species number is even smaller than that of Gordians, and so far only 5 species have been definitely established. Genus. Myrmis. Dujardin. Myrmith. Dujardin. Analyse des sciences naturelles, Orjototuan. P. 129. Character of the family. Myrmis albicans, V. Ziebold, Dutch. Plate 3rd. Fig. UI. 3. V. Ziebold, step. Entom, Zeit daughter, Yar G. 1850. P. 33. C. This. Cyst. 2. Helminth. Voldewer. P. 18. V. C. Bo. Owen. Zeitcher. Verwissensch. Zool. Voljadoli. VP 201. Meissner. Beeter. Zur Anat. Tort. U. Physio. Verwissensch. Der Myrmis albicans, in Zeitcher. Zool. Volju. This. VP27. Revis. Der Nematoden, in Sitzungsberichte der Matem, Naturwissenschaft, GL der Kais. AK.doi. Zuvin, Vol. 42, P607. Gordius phylum, Muller Inst. Verm. Terrester. Et fluvio. Voljuor. Gmel cyst, Nat Tord. 2. IP 31. P 3083. Vis. Cyst. 1. Helminth. Voljuor. 2 II. P 16. Est. Filaria acuminata, Rudolphi, Entosur. Nature.or. Valdesoden. P 66. .ry. EJ. Entors. Cyst.or. Synopsis P6. Dies. 2T. Helminth. Volju. Myrmis acuminata. P 109. Nat. Dorum. Filaria truncata. Rudolphi Entos. Hist. Tutoal. P 59. EJ. Entos. Synops. Y. Zeit, Yard. 1847. P5. Rosenhauer, Stet, Entom. P318. Planninger, Württemberg. 1852. Yari H.B. Tort. Heft 2. P205. Wiegmann's Archive. Faleria Succine, VZ, Baderorl, Bayerworm, Haweinor Baderlein. Yard. 1857. 2. P255. Dies. Sist. Wong. Helmet. Voldeur. Allo. Conwarding 1. Imdan P. P287. Myrmis Succinia. Autoplectus prognostus. Balsamo. Bibliothek. Ital. 1840. XCC. Doro. Mem. IR Instit. Lombard. DSG. Let. E. Ed Arty. 1843. P15. Figueroa. 115. Filaria lacustris. Dujardin. His. Nature. Des Helmintus. P68. Proter. PL Low. The third. Figueroa. F. Dies. D. Sist. Were. Helminth. Vol D. Bacto I. P112. Orta. Myrmis lacustris. Tail end blunt, in males enclosed by numerous papillae behind the genital opening. Length 2 to 5. Characteristic. Body tapered towards the front, milky white or transparent at the head and tail end with a rounded head. Lifestyle. The lifestyle is the same as mentioned for the family. I also encountered it in the honeybee, strangely only in the males. The worm occurs in the body cavity of various insects, which I consider unnecessary to list here. 64. In early August 1856, a true epidemic occurred among the drones of my beehives in Podolsk, Guv, Moscow, caused by the parasitism of this myrmis. Fall. In that year, the flow of nectar was good, and the hives kept the drones until September. After crushing one of the drones, I found a 3 to 5 long individual of the aforementioned myrmis within its body. After the drones had suffered from a strange lethargy and weakness for several days, the hives themselves remained in the beautiful and hottest days only marginally. I one day found several drones around the hives completely exhausted, and somewhere even lying dead, without having been forcibly removed from the hives by the bees, as happens in Thea. Later, after 3 days, many myrmidon were found on the ground around the stem, digging in the sand that covered the area, having emerged from the bodies of the drones. This helminthiasis lasted for another 12 days, making it a total of 15 days. After this period, the bees began to naturally expel the drones. I regret not paying more attention to this peculiar incident at the time, and, in particular, not examining some worker bees to see if they too had myrmidon. The worker bees, by the way, were healthy and active. Whether this questionable parasite was a nematode or belonged to the Gordian family, I cannot say. However, Professor Zenker cites a case in bee breeding from Klopfleisch and Kirschner 65 where, following Delabillardière, an endozoon was observed on a worker bee. All my attempts to find the mentioned article from Prof. Zenker and read it for myself were unsuccessful. Delabillardière classified it as the genus Dipodium, which I unfortunately do not know, nor do I have access to the relevant article by the author. The Bibliotheca Zoologica, edited by Professor Karras and Will Engelmann, as well as Dr. Hagen's entomological library, did not provide any insights on this matter. From the parasitism of myrmidon in male bees, I infer that these Gordiaceans, like the Gordians, could only reach the drones through passive migration. If the possibility exists that individual drones are forced to land on the earth by some chance, and thus might give young myrmidon an opportunity to bore into them, then it can only be considered a coincidence. They can also passively enter the working bee with the water they have sucked up, and through this reach the drone as mentioned for Gordius subafurcus. But if so many drones like those of my sticks had not been affected, then the myrmidon could also bore into the working bees, perhaps even better than into the Gordians, since the working bees frequently settle on the moist earth, which is the thesis habitat of the myrmidon, to suck up water. 66. World. The first migration of myrmidon is active, as Siebold has demonstrated with this species of myrmith, which invaded large numbers of the millimeter-long caterpillars of Iponomuta cognatella, and then migrating with the food pulp of the worker bee into the stomach of the drone larva, or fully developed drone. However, the second migration is definitely passive, as I also assumed for Gordius, because if the migration were merely active, the Gordiacine could only reach the drones if they first pierced through the outer shell of the worker bee to enter their body cavity, from there working their way through the intestinal membranes to reach the chylous stoma. Upon arriving here, they would need to pierce through the intestinal wall to establish their residence in the body cavity of the drone larva, or fully developed drone. This would be a very long and complicated migration, which is hardly plausible, till an insect swallows them with food. This does not seem quite so impossible to me as it perhaps appears. I therefore believe that the nematodes, like the Gordians, first become active within an insect, where they may also encapsulate themselves as those do. Then, after a certain period of time, they emigrate again, dispersing themselves as embryos not only in the earth but also on plants, their leaves, flowers, roots, etc., and thus awaiting chance for the proglottids of tapeworms leave feces, climb onto plants, and their offspring then reaches the intestines of herbivores with the plants. Shouldn't the embryo thus be able to enter the caterpillar's gut? Or would the caterpillar leave untouched the part of the leaf where the embryo is located? So one might imagine, to take just one example, a microscopically small Gordius or embryo of a myrmex attached to a leaf, which is then eaten by a caterpillar. Who knows if the embryos of Gordiaceans, following the analogy of other nemathelminths, for example, the ascarids, do not also possess the ability to retain their germinating power for a long time, even when dried out? Certainly not. Why then, shouldn't they swallow a Gordian embryo that is only 160 to 114 in size? For I have often seen voracious caterpillars, Pyrrhus brassicae, consume leaves with the skins of aphids, which can be clearly seen with the naked eye. An embryo swallowed by a caterpillar might perhaps only if the caterpillar is nearing pupation achieve its full development inside the pupa or the complete insect and emerge from it. And indeed, most Gordians encountered in insects with sucking mouthparts have reached their larval stage. Robinsectin are most easily infected with guardian worms when they consume an insect containing Gordiocene embryos. However, he did not continue his experiment. In one or several cases, the Gordian embryos might have been caught between the sharp jaws of these beetles, leaving them unable to develop. Meissner's experiment, as cited on page 137, involving the consumption of ephemeral larvae of water beetles, which were provided with Gordian embryos, and observing that the embryos were digested, contradicts the assumption of a repeated passive migration. Alternatively, the insisted Gordians may not yet have reached the stage where they could resist digestion in the stomach, a point Meissner himself hints at. Apistic significance. So far, the case stands only sporadically where myrmidon have been observed to be freeloading in honeybees and causing a true helminthiasis. On this point I have encountered them only in the drones, from which beekeepers can suffer losses only rarely, for example, when they need Italian drones to Italianize their colonies. However, since myrmidon cannot certainly reach the drones any other way than through the worker bees, it is certain that the worker bees are also infested by them. If the migration of myrmidon into the worker bees was passive, then in most cases the embryos will be expelled with the collected water, honey, etc., because the parasite will not be able to pierce through the gut membranes during the short time that the collected products remain in the bee's honey stomach. But the ingested materials are either used for brood feeding or remain in the chylous stomach of so-called food juice producers for an extended period. Appendix. And I even hold the view that bees are among the insects most prone to becoming infected with Gordiacid larvae, as honeybees scout for food everywhere and are not excluded from active migration either. In these cases, the larvae have ample time to emerge, and then bore through the gut to reach the body cavity. Thus, I believe that in some years, when myrmidon occur in large numbers, a good portion of worker bees die due to what is known as the so-called deadly disease resulting from this helminthiasis. Table 3. Fig. 5. I. p. 117. He classified it under the genus Hydrophora toda, or Mucor micheli, and named it Mucor melitophorus, ibid. Another little-known parasite of bees is a fungus from the Hyphomycetidae family Phaedon, or mold fungi, which Dr. Dunhoff 69 first discovered, and Professor Philibert, which was later described in more detail by Professor Philibert. Hedwigian note sheet for cryptogamic studies, Audiobook. I have never observed this fungus on my bees, so it remains unknown to me in nature. According to Lockhart, Dunhoff, and Hoffman, it occurs in the chilosoma of some bee colonies and enters from the outside, assuming, of course, that we exclude the phenomenon of spontaneous generation, which has recently gained renewed interest, especially among French naturalists as a spore with ingested material. The spore germinates here and forms itself into glassy threads with numerous branches on which sporangia develop, containing a kernly, slimy white content from which the spores finally emerge after ripening by bursting their very delicate sporogenous membranes, often appearing as spore clusters. This cluster gradually breaks down into a large number of colorless small spores that spread throughout the stomach and can also be found in the small and large intestines, while the actual fungus only occurs in the chylous stomach. This fungus is very prevalent among bees in many regions, particularly in Germany, as its spores can be transferred from one bee to another due to bees feeding their brood in each other. Illustration. Table I. Illustration. Table 2. In some beehives, the amount of pollen is so great that it often blocks the child gut with its spores, hindering nutrition and potentially causing a condition similar to rust, according to Lockhart 70 and Dunhoff 71. By the way, Kleinis 72 and von Berlepsch 73, whose bees were also affected by fungi, did not observe anything pathologic in their colonies. Illustration. Table 3. Footnotes. Male for males. 1. The symbol female is used by zoologists for females, and the symbol, the alleged dipteron, might be synonymous with Phora incrustata. 2. In the journal Lotus Journal for Natural Sciences, Volume 12, page 239, Dr. A list of bee parasites, actually insects that harm bees, is given, among which a new parasitoid, Phora apum, is included, which lays its eggs in the thorax of bees, probably bee larvae, and infests them until pupation, eventually leading to the bee's demise. 3. Compare my essay, Presumed Lifestyle of the Larvae of Ceropulpus barbatus shoal. Since these phorids named as a new species, but according to my knowledge, no such Phora apum exists, are not characterized, and nothing more is mentioned about them, I have not included them here. Viennese Entomological Monthly Journal, Vol. 3rd, 1859, p. 255. 4. Compare the classification of parasites in Leichhardt's Human Parasites, Vol. I, p. 6. 5. Compare Ratzenberg's Foreign Insects, Vol. I, p. 35. 7. Virgilio. 6. Spinola. Essay on Clarets, Vol. Sham. Catalogus Coleopterorum Europae, ed. Deset, p. 65. 8. Virgilio. Zeit Dotto. Zeb. Synopsis of the Coleoptera found in Germany so far stet. Entom. Yargi 13, p. 462. Also, Erichsen. Insects of Germany, 10th BD, ed. D. by Kiesenwetter, p. 674. Zeit.e. 9. Compare my article, Contributions to the Biology of Insects, Stet. Entom. Yard, 1863, p. 387. Annam. 10. Even the ancients considered this insect as living in beehives, naming it Prasicurus aristote. Hist. v. 19, 7. 11. Medicinal Zoology. Bauer. I. Issue I. 13. Structure of the Animal Body. Vol. 12. On the Natural History, Anatomy and Development of the Oil Beetle, Melloway, etc. Transactions of the Linnean Society, Vol. Trade, and Entium. 14. Ratzenberg in his Forest Insects, Vol. I. p. 111 lists cantharides as significantly harmful. Deep within, the benefit of this insect, outweighing the damage it causes by eating leaves from certain deciduous trees, is significant. 15. See Anton K. Chach, Pocketbook of Proven Healing Methods for Internal Diseases, 1857, p. 251. 16. Moreover, they do not only cling to bees but also ride on any other hymenopteran and insects from other orders that land on flowers, including many flies and even some beetles, such as Malachias, Telephorus, and others. But these larvae naturally all perish because they cannot enter the beehive, so it is likely that nature has arranged it so that this beetle family in particular exhibits such extraordinary fertility. 17. Memory on hypermetamorphosis and the habits of meloids. Annals of Natural Sciences, IV series, Volume 7, p. 356. 18. A similar kind of transformation has also been observed in a fly species Lonchoptera in recent times. 2. p. 80. 19. C. Schaum, Catalogus Coleopterorum, Europae edit. C. Lubbock, on the development of Lonchoptera in Transactions of the Entomological Society, 3rd series, p. 338. 20. C. Zeebe, Synopsis der bisher in Deutschland aufgefundenen Coleoptera Stettiner, Entomologische Zeitschrift, Year 13, p. 65. Et Histoire Nature, Tomte. 21. They were known by Goodart Metamorph. I. Tab. 1. De Geer, Abhandel, etc., translated by Goetze, B.D. Nat. Des Insectes, 1662, Tomletek, p. 180, Loschke, Naturforscher, 1788, 23, Frisch, Beschreibung von allerlei Insekten in Deutschland, B.D. Visit 14, Tafelvisit 2, T14, Tafelvisit, Valdol A. and IV, p. 248. Later, Hist. Des Krustak, Dort Dor. Et Ins, X 379, Reng, Annum. 22, as described by Kirby in his monography. De Cuvier, 3rd edit, 1836, the 3rd, 40, Nitsch, German Magaz, the 3rd, 5. Apum, Angliae, Vulture Tord. 2, p. 168. Tab, 14, under the name Pediculus Militea, du for Annales des Sciences Naturelles, Volume 13, under the name Triangulinus Tricospidatus, p. 17, or 23 on the natural history, anatomy and development of the oil beetle, Meloe, etc., Transactions Linnean Society, Volume 8, pp. 297, 321, Volume 21. 24. Memoir on the hypermetamorphosis and habits of meloids, D. Ppi, Annales des Sciences Naturelles, 4th series, Volume 299, Evol 9, p. 265. 25. Compare Brandt and Ratzeberg, Medic. Zoolog. p. 105, Dr. Bingrow. 27. As mentioned earlier, they also attach to other insects. 26. In my observations, the eggs develop after a period of 28 days. 28. Compare Schaum, Catalogus Coleopterorum Europae, EDN the 2 tie. p. 80. Stett, Entom, Zeit. 29. Zeebe, Synopsis of Coleoptera discovered in Germany so far. Year 14th, p. 65. N. 17. 30. Compare Kupf, Bienenzeitung, Year 14th, p. 191, and Gierson's Theory and Practice, Volume I, p. 581. The same Kupf lost in the year 1857 from his 23 hives 9 queens, and about half of the total working bees. 31. Bee Friend from Silesia, page 1077. If one now estimates the population of a hive at that time June to be only 15,000 on average, then the loss of working bees Kupf had to lament would have been 172,500, and this was caused by this insect. 32. This was already known to the ancients. According to him, in 1836, the whole of Silesia suffered from a fatal disease, with all the young bees of the hives perishing, and many a hive dying out entirely due to the loss of bees. They called it cholera, and believed that it occurred when bees collected products on which mold lay. In particular, it was said to occur in dry years. Aristotle, the 8th, 27, Ix 40. 19. Compare Magerstedt, Pictures from Roman Agriculture, Bite. page 207. 33 Kupf Bee Newspaper. Volume 14th, page Atwar, 191, and the confirmation of his observation of Siebold, Ibid. 34 Skinner, Catalogus Systematicus Dipterorum Europae, 1864, p. 48. Likewise Fauna Austriaca, Diptera, p. 335. 35 Skinner, OPCIT, p. 48. Also Fauna Austriaca, Diptera, p. 335. 36 Some overwinter under tree bark and in cellars, and can be found again in spring. 37 Development must take place already in the mother's womb. To my great regret, I was unable to properly examine the internal reproductive organs of the female. Only after several weeks did I take up this work again. Meanwhile, the flora specimens had become too much affected by alcohol, so I could not hope for a correct result. For the purpose of examination, I had thrown several living specimens of Phora incrustata female into alcohol, but was distracted from studying the Phoridae by another occupation that arose, so that the Phora females preserved in spirit fell into oblivion for a longer time. No fresh specimens were available to me. The fallopian tubes are moderately long. However, from the examination of these very damp specimens, it was determined that the two ovaries have an ear-shaped form, with the short oviducts arranged in 2 rows. The egg passage in the middle is only slightly expanded. The spermatheca is shaped like a pear. Other attachments could not be discovered. To obtain another result, I later softened dry specimens and submitted them to sectioning. 38 Beehiver's Newspaper, Volume 1851. In general, this examination confirmed previous observations, except that the fallopian tubes appeared significantly shorter. Page 20, page 182. 40 Bee Friend from Silesia, page 171. 39 Bees and Beekeeping in Areas with Little Honey, Mühlhausen, 1860. 41 On the Natural History of Bees. Bee Newspaper, Volume 1860, page 232. 42. Compare Volume 5 of the Bee Newspaper, pages 3 and 170. Also, Bee Friend from Silesia, page 173, and Rational Beekeeping, page 271. 43 Bee Newspaper, Volume 1849, pages 22 and 23. 44 Bee Newspaper, Volume 1864, page 53. 45. This was achieved in 4 attempts through effective smoking with chlorine gas. 46 V. Berlepsch, Bee Newspaper, Volume 1855, page 6. 47 Trech 13. 48 Shuai, 16. 49 Bee Newspaper, Volume 1849, page 2 and supplement, pages 83 F. 50 It is certainly very strange that wax was present among the distillation products. Incidentally, this is not the first time I have obtained wax from the dry distillation of insect larvae. So, I once subjected a larger quantity, 100 drachmas of collected cabbage-white butterflies, Pieris brassicae, to dry distillation, and soon obtained 65 grains of unwaxed wax at the beginning of the distillation. The same result, but in smaller amounts, was also achieved by the caterpillars of Pieris rapae and the larvae of Astynomus aedilis. Dr. Dunhoff, Bienenzeitung, Volume 1858, p. 204. According to Egger L.C., p. 46, they can run just as nimbly on the smoothest surfaces and glass walls as on the long-haired bodies of bees, which I, however, could only observe to be the opposite. Hammer confirms this in the same publication, p. 11. Bose, Bienenzeitung, 1858, p. 177. Gierzon, Bienfreund, p. 163. The latter counted 178 lice on a queen. When he cleaned the queen of the lice and returned her to the hive, she had 46 more after a few days. 55. In a peculiar way, I have not encountered any males so far. All specimens, even the smallest ones I examined around 100, were females. 56 compare with Berlepsch's The Bee and Beekeeping in honey-poor areas, p. 155, and Hammer L.C. 57 Egger, Contributions to a Better Understanding of Braulicoaca Niche, Proceedings of the Zoological Botany Society in Vienna, Volume 3, p. 405. 7, p. 1, Eft. I. 58 According to Schneider Archive for Anatomy and Physiology, 1860, p. 243. Meissner's meticulous investigations on Myrmis and Gordius from Siebold and Kulliker's Journal of Scientific Zoology, Vochel v. p. 27, and Volavite v. 27, and Voltral, regarding the nervous system have been proven entirely incorrect. 59 Charvet, Analyse des sciences naturelles des second, series, 60 Stettner Entomological Journal, Year 15, p. 104. 61 Proceedings of the Imperial Academy of Sciences in Vienna, Mathematical and Natural Sciences Class, Folio 42, p. 595. However, he does not rule out the possibility of a subsequent active migration, which I must reject for the reasons stated. 63. Compare Dujardin, Analyse des sciences naturelles, 1842, page 129. 62. This is also acknowledged by Meissner, as well as in page 137 of his work, and he relies specifically on the fact that the Gordian flies are not only found in aquatic insects, but mainly in terrestrial insects. 64. Compare Allgemeine Deutsche Naturhistorische Zeitung, year 1857, page 353. 65. The Bees and Beekeeping, Jena, 1836. ON. 66. Compare Stett. Da. Entom. Zeit. Year 1850, page 239. 68. Compare Leichhardt, Die menschlichen Parasiten, Volume Erd. 67. Siebold, in the aforementioned work, does not mention anything about the fate of the myrmidons that invaded the caterpillars of Hypanamuta cognitella. 69. Compare Bienen Zeitung, year 1857, page 66. 70. Compare Bienen Zeitung, year Certid, page 67. 71. Bienen Zeitung, year F. Same V, page 151. 72. Huber and Klein, volume 4, page 273. 73. The Bee and Beekeeping, etc., Pag, 151. Maigun. Transcription note. The following corrections were made, page 26, in the heading Fora Incrustata. The original does not italicize Maigun, but simply does not bold it. Headings corresponding to orders Coleoptera, Diptera, Gordiaceae are inconsistently formatted in the original and are treated uniformly here. The name Donovan was written as Donovan or Donau 3 times in the original, twice as Donovan. Other printing errors have been left as in the original template. Page 5, after proceed, add a period. Page 5. After Tom, I paid, 269. Add a closing parenthesis. Page 7. Replace end with wund. Page 8. Replace comma at the end of the paragraph with a period. Page 10. Replace Bienenimpfen with Bienenimpfen. Page 12. Replace Abgegesetzt with Abgesetzt. Page 14. Replace Vershennen with Vershein. Page 15. Replace Irrtümlich with Irrtümlich. Page 15. Instead of Dreisenrangelig, write Dreisenrangelig. Page 15. Instead of quadratisch, write quadratisch. Page 16. After Taif, add a period. Page 18. Instead of Weltteilen, write Weltteilen. Page 19. Instead of Konvulsionen, write Convulsionen. Page 22. Instead of 5 female, write 5 female. Page 23. Instead of Schwarzblau, write Schwarzblau. Page 24. Instead of Mittelgrosse, write Mittelgrosse. Page 27. Instead of Entwicklungsgeschichte, write Entwicklungsgeschichte. Page 29. Instead of Unterbrochen, write Unterbrochen. Page 29. Instead of Hautbedeckung, write Hautbedeckung. Page 30. Instead of Binnenstande, write Binnenstande. Page 31. Instead of Beobachtet, write Beobachtet. Page 36. Instead of Bienen, write Bienen. Page 32. Instead of Zersetzungsprozess, write Zersetzungsprozess. Page 37. Instead of Nachträglichen, write Nachträglichen. Page 43. Instead of Ingredienzien, write Ingredienzien. Page 43. Instead of Ablager, write Ablager. Page 49. After to a third. Fig. Tum. Male, for female. Complete the closing bracket. Page 52. Instead of Filaria, read Filaria. Page 55. Instead of Gordiocynimbrionen, read Gordiocynimbrionen. Page 56. Instead of Weissgeblichen, read Weissgelblichen. Footnote 3. Complete the closing bracket at the end. Footnote 14. Add a period at the end. Footnote 17. Instead of Meloides, read Meloides. Footnote 18. Instead of development, read development. Footnote 23. Instead of oil beetle, read oil beetle. See footnote 12. Footnote 36. Instead of M, read M. Footnote 24. Instead of Lipermetamorphose and Meloides, read Lipermetamorphose and Meloide, and complete the closing bracket. End of Project Gutenberg's Parasites of the Honeybee by Dr. Eduard Assmuss.